Pipe dream. Pirate first.
Pipe dream part 7. Safety first. Chapter 1, Breakaway architecture. Safety engineering in the surface world is organized around a premise so deeply embedded in the discipline's foundations that it has achieved the status of invisible assumption: the structure should not fail. The engineer's obligation to safety is the obligation to design against failure, to specify materials that will not fracture, connections that will not separate, systems that will not lose function, and components that will not reach the end of their service life before the maintenance protocol has been executed to restore them. The structure's failure is the safety system's failure. The safety system exists to prevent the structure from failing. This premise is operationally coherent for most of the surface world's structural engineering contexts. A bridge that does not collapse is a bridge whose safety engineering succeeded. A building that does not fall is a building whose safety engineering succeeded. A pressure vessel that does not rupture is a pressure vessel whose safety engineering succeeded. In these contexts, the structure's failure is the catastrophic outcome that the safety engineering must prevent, and preventing it is a tractable engineering problem whose solution involves specifying materials and dimensions and inspection protocols that the structure can maintain across its design life without reaching failure conditions. The cenote network is not this context. The cenote network is a geological system that will produce formation events, microseismic activity from the Chicxulub fracture network, dissolution events in the limestone supporting the crystal tube's anchor zones, hydraulic events from the underground river system's flood accommodation conditions, that are not preventable by any engineering specification, not predictable at the resolution required to prevent their occurrence at specific times and locations, and not manageable through material or dimensional specification alone. The formation will do what the formation does. The formation event that produces a ceiling collapse in a passage section, or a wall dissolution that undermines an anchor pylon's limestone substrate, or a hydraulic flood event that drives the water table above the cenote rim's structural capacity, these events are not the safety system's failure to prevent. They are the formation's geological behavior, continuing on the geological timescale that has been producing these events since 66 million years before the civilization arrived. Pipe dream's safety architecture is organized around a different premise: not the structure should not fail, but the structure should fail correctly. The distinction is not semantic. It determines the entire architecture of what Part 7 documents. A structure designed not to fail is a structure whose safety investment is concentrated in preventing the first failure event. When the first failure event occurs, and in a geological environment operating on geological timescales across a 1,000-year design life, the first failure event will occur, the structure is encountering a condition its safety specification did not prepare it for. The failure produces the consequences of a structure that was not designed for failure: unpredictable failure mode, unpredictable failure extent, potentially catastrophic cascade from a localized failure into a network-wide loss of atmospheric integrity. A structure designed to fail correctly is a structure whose safety investment is distributed across preventing catastrophic cascade, containing failure within designed boundaries, and converting every failure event into a data point that improves the formation model. The failure is not prevented. The failure is managed toward the specific mode, at the specific location, with the specific consequences that the safety architecture was designed to produce. The failure's occurrence is not a safety failure. The failure's departure from the designed failure mode is the safety failure. This is breakaway architecture, the design of structural elements whose failure mode is specified as precisely as their operational performance, deployed at designed locations within the network for the purpose of producing designed failure when the formation produces the event that the operational specification could not prevent. The discrete segment isolation principle. The crystal tube network's most fundamental safety property is the discrete segment isolation principle. The network is designed to absorb the simultaneous failure of any number of individual sections without cascading into network-wide loss of atmospheric integrity. DSI is not a property that emerges from the network's geometry. It is a property that is designed into the network's geometry, that requires specific structural provisions at specific locations within the network to exist, and that requires every structural connection between adjacent sections to be evaluated for its DSI compatibility at the design stage rather than at the failure event's occurrence. The DSI principle's challenge is that the crystal tube network's most valuable operational property, the continuous atmospheric enclosure that allows the transit pod's maglev propulsion system to function, that maintains the longevity program's therapeutic pressure in the residential zones, and that allows the scaphandre participants exchange with the wetlock's docking port, requires that adjacent sections be continuously connected. The continuous connection is both the network's operational prerequisite and the cascade failure's propagation mechanism, the same connection that allows the atmospheric management system to maintain therapeutic pressure throughout the residential zone allows a breach event in one section to propagate pressure loss to all connected sections. DSI resolves this by segmenting the continuous connection into sections whose boundaries are the passive isolation points, the locations where the formation event's cascade is designed to stop. The segmentation must not impair the operational continuity within each segment. The isolation must not require operational intervention to activate, it must be passive, physics-driven, and faster than any alternative that requires sensor detection and control signal transmission. The two structural provisions that implement DSI in the crystal tube network are the sacrificial collar and the passive hydraulic rotary gate. They are not redundant provisions, they are sequential provisions, each addressing a different phase of the failure event's propagation. The sacrificial collar addresses the kinetic energy propagation phase. The passive hydraulic rotary gate addresses the fluid intrusion phase. The two together produce the segmentation that DSI requires. The collar decouples adjacent sections kinetically before the gate seals the breach hydraulically. The sacrificial collar. Every 100 meters along every tube in the network, a sacrificial collar interrupts the structural continuity of the crystal tube wall. Not the functional continuity, the atmospheric management, the guide rail, the utility conduit, the light relay's internal surface, these all traverse the collar without interruption. The structural continuity of the tube wall material is interrupted at the collar's position by a section of material whose mechanical properties differ from the adjacent tube wall material in a specific and precisely specified way. The adjacent tube wall material, polycarbonate, PMMA, aluminosilicate glass, alone, or borosilicate carbon composite depending on the depth zone, is selected for its operational performance across the full range of loads the tube's functional specification requires it to resist. It is specified to resist these loads at the maximum values the geological model predicts across the design life, with the safety factor the founding charter's structural specification requires. The sacrificial collar's material is selected for a different objective. Not maximum resistance to the geological model's predicted loads. The precise failure threshold, the kinetic energy level at which the collar material fails in the specific clean shatter mode that the DSI principle requires, decoupling the affected section from the adjacent sections without transmitting the failure's kinetic energy forward. The collar material is a frangible ceramic composite, high tensile strength, low impact toughness. The tensile strength specification ensures that the collar does not fail under the loads the tube's operational specification produces, the hydraulic pressure differential across the tube wall in normal operation, the thermal gradient stress the depth zone's temperature cycling imposes, the hoop stress from the guide rail's anchor loads transmitted through the tube wall. These operational loads are sustained by the collar without failure. The collar is not frangible under operational loads. The impact toughness specification ensures that the collar fails under the kinetic energy load that a formation event produces, the energy of a ceiling collapse propagating along the tube, the energy of a wall dissolution event that severs the tube's anchor connection and allows the tube section to impact the passage wall, the energy of a hydraulic wave from a flood event that impacts the tube section's end. These are impact loads, loads delivered rapidly, at high energy, that are absorbed by the material's fracture rather than by its elastic deformation. High impact toughness absorbs the fracture energy and transmits the residual energy forward. Low impact toughness, the collar specification, fractures cleanly at the impact energy's first threshold, absorbing the fracture energy in the fracture itself and transmitting minimal residual energy to the adjacent section. The collar's failure is the decoupling event. The adjacent section, whose collar was the kinetic coupling between it and the affected section, is kinetically decoupled from the affected section at the collar's failure moment. The formation event's kinetic energy has been absorbed in the collar's clean fracture. The adjacent section receives the residual energy below the collar's failure threshold, the energy that the collar did not absorb, rather than the full event energy that would have propagated without the collar. The collar's failure is observable in the piezoelectric sensor network's acoustic signature within milliseconds of the fracture. The collar's fracture produces a characteristic acoustic event that the coordinating system's geological monitoring layer identifies as a collar failure event rather than as a geological acoustic event. The frequency spectrum, the amplitude profile, and the temporal structure of the fracture acoustic event are distinct from the geological events that the formation produces and from the operational acoustic events that the tube network's biological and mechanical maintenance activity produces. The coordinating system identifies the collar failure event's location from the differential arrival times at adjacent transceiver nodes and logs the event in the digital twin's construction record as a geological data point. The collar failure is not an incident to be investigated as a safety failure. It is a geological observation to be analyzed as a formation intelligence data point. The collar failed because the formation produced a kinetic event at this location that exceeded the collar's failure threshold, and the formation's production of this event is information about the geological state of the Chicxulub fracture network at this location at this moment. The information is in the digital twin. The geological model is updated. The structural monitoring's prediction for adjacent sections is revised to account for the identified stress concentration. The boring program's advance rate is adjusted in this zone if the model's revision indicates elevated geological activity. The collar failed. The collar performed its function. The failure is the performance. The collar's geometry. The collar's physical geometry is the critical determinant of its failure mode's cleanliness. A collar that fractures into large irregular fragments produces a debris field that the passage water carries as suspended particulate, The particulate that the siltback's maintenance protocol eventually removes from the passage floor but that in the immediate post-fracture period reduces the visual field through the adjacent section's hull material and potentially interferes with the autonomous harvest drones and maintenance subs' navigation in the affected passage zone. The collar's geometry is designed to produce small, uniform, rapidly settling fracture fragments rather than large, irregular, slow-settling ones. The frangible ceramic composite's crystal microstructure, the grain size distribution and the crack propagation resistance at the grain boundary chemistry, is specified to produce fracture at the grain boundary scale, fracture that propagates preferentially along the crystal grain boundaries rather than through the grain interiors, producing fragments whose characteristic dimension is the grain boundary spacing rather than the macroscopic geometry of the collar. At the frangible ceramic composite's specified grain boundary spacing, the fracture fragments are small enough to settle through the freshwater column's water density to the passage floor within minutes of the fracture event. The water clarity at the affected section returns to near normal within the settling time. The visual field through the adjacent section's hull is impaired for minutes rather than hours. The biological community's behavioral disruption from the particulate disturbance follows the suspended particulate's settling curve and returns to baseline within the settling time plus the behavioral recovery time the species-specific behavioral monitoring protocol specifies. The collar's fracture fragment size is an ecological specification as well as a structural one. The collar fails cleanly not only to decouple the adjacent sections kinetically but to minimize the ecological impact of the failure on the freshwater zone's biological community. The clean failure that produces small settling fragments is the failure mode that the ecological impact budget's emergency allowance specifies for collar failure events. Failure modes that produce large non-settling fragments, that would require mechanical removal by the siltback's extended cleaning protocol rather than passive settling, are failure modes the collar geometry specification explicitly excludes. The specification of the failure mode's ecological impact is the Breakaway architecture's most distinctive safety engineering feature, a safety component whose failure performance standard includes ecological impact criteria alongside structural and kinetic criteria. The surface world safety engineering does not specify failure mode's ecological consequences as a design parameter. Pipedream's safety engineering does, because Pipedream's safety architecture cannot be separated from the biological management protocol that operates in the same physical environment the safety architecture is managing failures within. The collar's placement logic. 100 meters is the collar spacing that the founding engineers specified after the design optimization exercise that the geological model's microseismic activity data supported. The spacing logic addresses two simultaneous constraints: the minimum spacing that provides adequate section length for normal operations, and the maximum spacing that keeps the kinetic energy transmission distance below the threshold at which the transmitted energy's residual would cause secondary collar failures in the adjacent sections. The minimum section length constraint is operational, a crystal tube section that is too short to accommodate the standard transit pod's length, the standard junction node's diameter, and the standard utility conduit's connections at both ends is a crystal tube section that cannot perform the operational functions the crystal tube standard specifies. The minimum section length is determined by the largest operational element that must fit within a single section. In the current standard configuration, the transit pod's length at the maximum configuration, with the safety margin the coordinating system's transit management layer requires for the pod's deceleration distance within a section. The maximum spacing constraint is safety-specific. The kinetic energy that a formation event produces at the geological model's worst-case event magnitude propagates along the tube at a rate that the frangible ceramic composite's acoustic propagation characteristics determine. The maximum distance over which this propagation rate can transmit the worst-case event's energy above the secondary collar failure threshold, the energy level that would cause the collar at the spacing distance to fail, defines the maximum collar spacing that prevents cascade collar failures from a single formation event. At the geological model's worst-case event magnitude derived from the Speleothem paleoclimate record's historical extreme events, and the frangible ceramic composite's acoustic propagation characteristics, the maximum cascade-free spacing is approximately 115 meters. The specified 100-meter spacing provides a 15% margin below the cascade-free maximum, the same class of safety margin that the structural specifications throughout the crystal tube standard apply to all safety-critical dimensional parameters. The 100-meter spacing was also informed by the practical consideration that the coordinating system's collar failure location identification algorithm, which triangulates the failure location from the differential acoustic arrival times at adjacent transceiver nodes, requires the collar failure's acoustic signature to arrive at least two adjacent transceiver nodes with different arrival times. Two nodes at the transceiver chain's 50-meter standard deployment interval are always within 100 meters of any collar position, ensuring that every collar failure event produces the two-node timing differential that the location identification algorithm requires. The collar spacing determines safety engineering requirements. The collar spacing satisfied the acoustic monitoring architecture's data quality requirements simultaneously. One dimension, two requirements, both satisfied. The engineering constraint and the monitoring architecture's requirement converged on the same spacing because they are both derived from the same physical system's characteristics, the acoustic propagation in the cenote's water column that both the kinetic energy transmission and the transceiver chain signal transmission use. The collar as geological instrument. The collar failure event's geological data contribution was introduced in the structural discussion above. The failure is a data point that the geological model incorporates as evidence of the formation's current stress state at the failure location. But the collar's geological instrumentation function extends beyond the failure event itself to the continuous monitoring that the collar's material properties enable between failure events. The frangible ceramic composite's acoustic transmission properties, the way acoustic energy propagates through the collar material at frequencies below the failure threshold, are distinct from the adjacent tube wall material's properties. The collar's acoustic signature in response to the piezoelectric network's routine monitoring pulses provides a continuous measurement of the collar material's current stress state. The acoustic transmission profile changes as the collar material accumulates stress below the failure threshold, with specific frequency components in the acoustic response shifting in amplitude and phase as the internal stress field alters the material's acoustic propagation tensor. The coordinating system's geological monitoring layer maintains a baseline acoustic transmission profile for each collar in the network, established during the collar's installation commissioning survey. The baseline represents the collar's acoustic transmission profile in the stress-free condition, the acoustic signature the collar produces when the formation has not loaded it above the operational stress that the crystal tube's normal operational loads produce. Any deviation from this baseline in the collar's routine monitoring response indicates that the formation is applying stress to the collar above the operational baseline, that the geological system is loading the collar toward its failure threshold from the direction of the geological event that has not yet reached failure magnitude. The pre-failure stress accumulation in the collar is detectable in the acoustic monitoring data before the collar reaches its failure threshold. The detection is not a precise warning. The acoustic transmission sensitivity to pre-failure stress accumulation provides a qualitative signal that the collar is in an elevated stress state, not a precise prediction of the time to failure or the event magnitude that would produce failure. But the qualitative signal is sufficient to trigger the coordinating system's enhanced monitoring protocol for the collar's vicinity, higher frequency acoustic monitoring pulses, terraform operator notification, boring program advance rate reduction in the adjacent geological zones, that prepares the network for the collar failure that the stress accumulation indicates is more likely than the geological model's ambient prediction. The collar is the network's distributed geological stress sensor array. One collar every 100 meters across the full crystal tube network extent is the geological monitoring system's most spatially comprehensive sensor, not because the collar was designed as a sensor, but because the collar's material properties make it responsive to the pre-failure stress accumulation that the geological events produce, and the coordinating system's acoustic monitoring is measuring the collar's acoustic transmission profile at every monitoring interval for structural health. Purposes that simultaneously serve the geological monitoring function. This dual function, structural health monitoring and geological stress sensing, is the Breakaway architecture's most sophisticated operational contribution to the formation intelligence program. The safety components that were specified to fail correctly are also the geological instruments that detect the approaching conditions that will cause them to fail. The safety system is the warning system. The warning system is the safety system. They are the same components doing two functions simultaneously, as all of PipeDream's design systems tend to be. The collar and the biological community. The collar's failure produces an acoustic event that the freshwater zone's biological community detects through the lateral line systems, the auditory organs, and the pressure receptors that the cenote species have evolved to respond to seismic and hydraulic events in the karst environment. The detection is not the collar failure's ecological impact. The collar failure's acoustic event is within the amplitude range of the natural geological events that the cave fauna's evolutionary history has equipped them to respond to. The detection triggers the natural behavioral response, the cave fish community's brief schooling disruption and retreat to the structural shelter of the synthetic reef community, the Bodo population's temporary acceleration out of the affected passage zone, the Ancestris vitreous colony's brief interruption of the cleaning behavior before resumption. These behavioral responses are transient. They are the biological community's evolved response to the acoustic events that the karst environment produces naturally, expressed in response to the collar failure's acoustic event because the collar failure's acoustic signature is within the range the biological community's sensory systems are calibrated to respond to. The responses resolve within the behavioral recovery times the species-specific behavioral monitoring protocol specifies, which for all freshwater zone species are measured in minutes to tens of minutes rather than in hours or days. The collar failure's transient biological impact is within the ecological impact budget's emergency allowance, the ecological impact tolerance the founding charter's visitor management protocol reserves for the formation events that the conservation standard cannot prevent through the visitor activity management that the standard normally controls. The emergency allowance exists because the formation's geological behavior is not within the visitor management's control. The formation produces collar failure events when the formation stress state produces them. The ecological impact that the collar failure events produce is the geological event's ecological cost, managed through the emergency allowance rather than through the visitor program's pre-event ecological impact management. The Terraform operator's concurrent authority in the post-collar failure assessment is the human judgment about whether the collar failure's biological impact has resolved within the emergency allowance's tolerance before visitor program activities are restored to the affected zone. The coordinating system's biological monitoring provides the species-specific behavioral recovery indicators. The Terraform operator's concurrent authorization confirms that the indicators are within the recovery tolerance before the zone's visitor program quota is restored from the post-event restriction that the coordinating system's automated visitor management layer applies immediately upon the collar failure event's detection. The visitor management layer's automated restriction is the visitor program's instantaneous response to the collar failure. The affected zone's visitor activity is suspended, cycle sub-transits rerouted, scavenger sessions terminated and participants directed toward the nearest wetlock docking port, safari routes redirected, within the time the coordinating system requires to identify the collar failure's location from the acoustic arrival timing and activate the visitor management. Restrictions for the affected zone's neighboring crystal tube sections. The restriction is activated before any visitor activity assessment could determine whether the specific collar failure's impact warrants the restriction. The restriction is automatic and precautionary. The Terraform operator's authorization restores activity when the assessment confirms recovery. The automatic precautionary restriction and the Terraform operator's authorized restoration are the human-machine division of authority that the REDIMA governance framework safety architecture specifies for formation event responses. The coordinating system's automated response is immediate and precautionary. The human's authorized response is delayed and informed. The coordinating system does not wait for human authorization to restrict. The human does not restore without coordinating system assessment data. The sequences: automatic restriction, biological assessment, Terraform operator authorization, quota restoration. The sequence's integrity is constitutional. No step in the sequence can be bypassed by any authority the principality recognizes. The collar's legacy. A collar that has failed is a collar that has performed its function. It is not replaced with a collar of identical specification at the failed position. It is replaced with a collar whose specification has been updated to reflect the geological data the failure event generated about the formation stress state at the failed location. The updated specification may be identical to the failed collar's specification if the geological model's analysis of the failure event determines that the event was within the range the existing specification was designed for, and that the existing specification's safety margin was appropriate for the location's geological conditions as now better understood. Or the updated specification may differ from the failed collar's specification in one of two directions: higher failure threshold if the geological model's analysis determines that the failure event's energy was below the specification's design intent due to the collar's manufacturing variance toward the low end of the specification's tolerance range, or lower failure threshold if the geological model's analysis determines that the formation stress state at the failed location indicates higher than predicted geological activity that the updated collar should respond to at lower kinetic energy. The collar replacement specification update is the geological model's management of the network safety architecture across the design life, not a fixed specification that all collars in the network share regardless of the geological conditions at each collar's location, but a location-specific specification whose value reflects the geological data that the collar's service history and the acoustic monitoring's pre-failure stress accumulation record have provided about the formation's behavior at that specific location. The 100-meter spacing is constant. The failure threshold specification at each location is not. The network safety architecture becomes more precisely calibrated to the formation's geological character at each location with each collar failure event and each collar replacement. The safety architecture improves with the formation's geological self-expression. The formation's geological behavior is the safety system's training data. A safety system trained by the geological behavior it is designed to manage is a safety system that improves with the formation's history. At year 1, the safety architecture's collar specifications are derived from the geological model's predictions. At year 500, the safety architecture's collar specifications at each location are derived from the geological model's predictions as refined by 500 years of formation events at those specific locations. The precision is incomparably higher. The safety margin is commensurately better calibrated. The safety architecture at year 500 is not the founding years architecture applied for 500 years. It is the founding years architecture trained on 500 years of formation events into the formation-specific safety architecture that the founding years architecture was designed to produce. The 1,000-year design life safety architecture improves toward precision across the design life. This is the Breakaway architecture's most significant safety property and the one that has no surface world equivalent, a safety system that uses its own operational events as training data for its own specification improvement. The collar fails. The failure is data. The data improves the specification. The improved specification produces better calibrated collars. The better calibrated collars produce cleaner failures whose data is more precise. The precision compounds. The surface world safety engineering improves through research and regulatory update, external processes that apply new knowledge to specifications through institutional channels that can take years or decades to produce field changes. Pipedream's breakaway architecture improves through operational experience at the formation, internal processes that apply the formation's own geological expression directly to the specification through the coordinating system's geological model update and the replacement collar's specification revision. The improvement timescale is the geological model's update cycle, which is the next collar replacement opportunity. Weeks to months, not years to decades. The formation teaches the safety architecture faster than any external research program can. The network geometry's safety architecture. The collar's placement at 100-meter intervals along each tube section is the safety architecture's linear provision. The crystal tube network's three-dimensional geometry, the junctions, the hub connections, the depth variable connections, intermediate refuge stations, introduces nonlinear safety provisions that the collar spacing does not address, the formation events that affect the three-dimensional network's nodes rather than its linear segments. A junction node, the chamber where two crystal tube sections from different intersynody connections meet, is a three-dimensional structure whose failure mode is not the clean collar fracture that a linear section's geological event produces. A junction node's failure involves the failure of the chamber structure itself, which is a more complex three-dimensional failure mode than the linear section's collar fracture. The junction node's safety specification is correspondingly more complex, not a single collar at a specific position, but a distributed frangibility design that provides the DSI principle's decoupling function across the junction node's three-dimensional geometry. The junction node's distributed frangibility design is documented in the Crystal Tube Standards Appendix D alongside the collar specification, and its full treatment is the subject of Part VII's Chapter 3, Compartmentalized Cities. The current chapter establishes the breakaway architecture's foundational principle, designed failure modes at designed locations, as the intellectual framework within which Chapter 3's three-dimensional safety provisions operate. The hub connection safety provisions are the network's most complex three-dimensional safety engineering. The Cenote hub structural connection to the crystal tube network involves the transition from the hub's full atmospheric volume to the crystal tube's confined volume, across a structural boundary that must accommodate the hub's atmospheric management loads, the crystal tube's operational loads, and the formation event's kinetic energy transmission from the crystal tube network into the hub structural mass. The hub connection safety architecture concentrates the formation event's kinetic energy from the crystal tube's linear direction into the hub's three-dimensional mass through a specific structural interface geometry that the founding engineers specified to produce the kinetic energy's dissipation into the hub's mass rather than its reflection back into the crystal tube network or its transmission through the hub into the adjacent crystal tube section. The interface geometry is an acoustic impedance mismatch, a design structural discontinuity at the hub crystal tube interface whose acoustic impedance profile dissipates the formation event's kinetic energy in the discontinuity rather than transmitting it. The acoustic impedance mismatch is the safety physics of the hub connection's designed failure behavior, not a collar that fractures cleanly, but an interface that absorbs kinetic energy through wave reflection and dissipation. The interface does not fracture. It dissipates. The distinction is important. A fracturing collar produces fragments that must settle, a dissipating interface does not. The hub connection safety design produces no debris. The kinetic energy is absorbed in the interface's structural mechanics without producing the material failure that the collar's frangible fracture produces. The hub connection's dissipative interface is the safety architecture's most sophisticated structural element because it must simultaneously serve the operational requirement, a structural connection that maintains the atmospheric enclosure between the hub and the crystal tube across the full operational load range, and the safety requirement, a dissipative barrier that absorbs the formation event's kinetic energy at the event magnitude threshold above the operational range. The same interface geometry that provides the structural connection provides the energy dissipation. The operational and safety functions share the same structural element, as they share the same structural element in the collar's dual operational geological sensor function. The breakaway architecture is not a parallel safety system installed alongside the operational system. It is the operational system designed with the safety function specified as precisely as the operational function, so that the structural elements that provide operational performance simultaneously provide the safety performance the formation requires. Failure as information. The breakaway architecture's defining intellectual contribution to Pipedream's safety engineering is the reclassification of failure from an outcome to be prevented into an event to be designed. The surface world safety engineering treats failure as the enemy, the outcome the safety system's entire investment is directed toward preventing. Pipedream's safety engineering treats failure as the formation's communication, the geological event that the formation has produced, expressed in the safety system's designed response, recorded in the digital twin as geological data. This reclassification has governance implications as significant as its engineering implications. The Amazon installation's safety engineering failed not because its structural specifications were inadequate, the structural materials were correctly specified for the formation's geological conditions, the maintenance protocols were correctly calibrated to the formation's material degradation rates, The monitoring systems were correctly designed to detect the formation's stress events at the temporal resolution the safety engineering required. The Amazon installation failed because its governance architecture reclassified the variance reports that the safety monitoring generated. The formation produced the signals. The safety monitoring detected the signals. The governance architecture decided the signals were not signals. Pipedream's governance architecture cannot reclassify collar failure events as non-events. The collar failure is a geological data point that the digital twin records, that the geological model incorporates, and that the replacement collar specification reflects. The reclassification requires the digital twin's falsification, the removal of the geological data point from the digital twin's formation record. The digital twin's common status, whose modification requires the Network Governance Council's authorization and the Research Commons concurrent review, makes this falsification constitutionally impossible within the principality's legal framework. The formation event that breaks the collar is the formation asserting its geological reality. The digital twin that records the collar failure is the civilization's institutional acknowledgement of that reality. The replacement collar's updated specification is the safety architecture's response to that reality. The sequence is the Constitution's enforcement mechanism for the Founding Charter's fundamental commitment: the formation is always right. The data from the formation is always incorporated. The specification is always updated to reflect the formation's expressed geological character. The breakaway architecture is the physical implementation of this commitment at the structural level. The collar that fails correctly records the failure's data and is replaced with a collar whose specification reflects the formation's data. The commitment at the governance level, the constitutional protection of the digital twin's integrity that prevents the formation's data from being reclassified, is what makes the breakaway architecture's physical implementation meaningful rather than cosmetic. A safety system that fails correctly but whose failures are reclassified as non-events is the Amazon installation's architecture. A safety system that fails correctly and whose failures are constitutionally protected as geological data is Pipedream's architecture. The difference is not in the collar. The difference is in what happens after the collar fails. What the breakaway architecture produces. The Crystal Tube network at year 500 is a network whose safety architecture has been trained by 500 years of collar failure events distributed across the full network extent. The training is not uniform. Some locations have produced multiple collar failure events within the design life, developing a detailed geological characterization that the collar specification's iterations have refined to a location-specific precision. Other locations have produced no collar failures, accumulating the pre-failure stress accumulation record that the acoustic monitoring has maintained without reaching the failure threshold in 500 years of formation events at those locations. The network's safety architecture at year 500 is therefore a geological portrait of the formation's 500-year stress history, expressed in the location-specific collar specifications distributed throughout the network. A geologist who reads the collar specification map, who notes which locations have higher failure thresholds, indicating formation stability at those locations across the design life period, and which have lower thresholds, indicating formation activity that the geological model's historical analysis has characterized as recurring at magnitudes requiring the lower threshold sensitivity, is reading the formation's geological character expressed in the safety architecture specification. Distribution. The collar specifications are the formation's autobiography, written in the engineering language of failure thresholds and crack propagation coefficients and acoustic impedance profiles. The formation told the coordinating system what it does at each location. The coordinating system wrote the specification that expresses what the formation said. The collar installation reflects the autobiography. The collar failure event continues the autobiography. The safety architecture is not protecting the civilization from the formation. It is listening to the formation, continuously, at every collar's acoustic monitoring interval, at every collar failure event, at every geological model update, and responding to what the formation says by adjusting the specifications that the civilization's structural presence in the formation produces. The collar fails when the formation speaks above a certain volume. The collar is replaced with a collar that listens at the right threshold for the formation's voice at that location. The formation continues speaking. The collar continues listening. The network continues operating. This is the breakaway architecture's deepest engineering character. It is not a barrier between the civilization and the formation. It is a medium through which the formation and the civilization communicate about the geological conditions that both the formation and the civilization share. The civilization is inside the formation. The formation's geological events are the formation's communication about its own state. The safety architecture is the language the civilization has developed to hear what the formation is saying and respond correctly. The collar does not protect the civilization from the formation. The collar translates what the formation is saying at this location at this moment into a structural event, the clean fracture, the kinetic decoupling, the acoustic signature, the geological data point, that the coordinating system can read and the safety architecture can respond to. The translation is the safety system's function. The civilization is safe because it listens to the formation. The breakaway architecture is the listening mechanism. The collar is the listening mechanism's most widely distributed, most geologically specific component. Cross-references, Part 1, CH4, Floating Before Anchoring, Part 2, CH4, The Crystal Tube Standard, Part 2, CH6, Designing for 1,000 Years, Part 3, CH1, Rivers Beneath the Jungle, Part 4, CH2, Autonomous Construction, Part 7, CH2, Automatic Bulkheads, Part 7, CH3, Compartmentalized Cities, Part 7, CH4, Living Through Failure, Part 7, CH5, The Blackout Protocol. For sacrificial collar material specification, grain boundary chemistry requirements, and failure threshold calibration protocol, see Appendix D, Construction Operations Manual. For collar failure event location identification algorithm and geological model update protocol, see Appendix G, Formation Intelligence Record. For post-collar failure visitor management restriction parameters and Terraform operator restoration authorization procedure, see Appendix H, Governance Operations Manual. For collar replacement specification update methodology and geological data integration, see Appendix G, Formation Intelligence Record. For hub connection acoustic impedance mismatch design specification, see Appendix D, Construction Operations Manual. Chapter 2, Automatic Bulkheads. The problem with sensor-activated safety systems is the sensor. The sensor must detect the condition that requires activation. The sensor must transmit the detection to the control system. The control system must process the transmission and issue the activation signal. The activation mechanism must receive the signal and operate. Each step in this sequence requires time, the detection latency, the transmission latency, the processing latency, the actuation latency. The sum of these latencies is the sensor-activated system's response time, the interval between the condition's onset and the safety mechanism's activation. In most engineering contexts, this response time is inconsequential relative to the hazard's development timeline. A building's fire suppression system's response time of seconds is inconsequential relative to a structural fire's development timeline of minutes. An aircraft stall warning system's response time of milliseconds is inconsequential relative to the aerodynamic stall condition's development timeline of seconds. The sensor-activated safety system's response time is shorter than the hazard's development time, and the safety system reaches its activation state before the hazard reaches the catastrophic threshold the safety system exists to prevent. In a crystal tube breach event, the response time calculation produces a different relationship between the detection timeline and the hazard's development timeline. A breach event, a structural failure that opens the crystal tube's atmospheric enclosure to the cenote's water column at the breach location, begins admitting water at the rate the hydrostatic pressure differential between the cenote water at the breach depth and the crystal tube's internal atmospheric pressure drives. At 30 meters depth, this differential is approximately 3 atmospheres, 3 times the pressure of the atmospheric enclosure's internal pressure. Water enters at the rate 3 atmospheres of pressure differential drives through the breach geometry. The initial breach geometry is small. The formation event that produces the breach typically produces it as a fracture that propagates through the tube wall in a crack whose initial dimension is at the millimeter to centimeter scale. At this scale, the inflow rate is manageable. The atmospheric management system's pressure supply can compensate for the inflow at initial breach dimensions. But the breach geometry does not remain at initial dimensions. The hydrostatic pressure differential applies structural loading to the breach's crack tips that propagates the crack in the tube wall material's weakest direction. In the microseconds following the initial breach, the crack propagates, rapidly, at the acoustic velocity in the tube wall material, toward the tube wall's structural failure threshold. The structural failure threshold is the tube wall's fracture toughness, the resistance to crack propagation at the crack tip that the material's microstructure provides. Below the fracture toughness, crack propagation is stable. The crack extends but at a rate that the applied loading determines, and reducing the loading reduces the propagation rate. Above the fracture toughness, crack propagation is unstable. The crack extends faster than the loading can be modified, reaching the tube section's full circumference in milliseconds and producing the catastrophic breach that the safety architecture's DSI principle must isolate within the affected section. The sensor-activated safety system's response time, seconds in the fastest electronic implementations currently available, is longer than the interval between the initial breach and the catastrophic breach in the tube wall material's unstable crack propagation regime. A sensor that detects the initial breach and transmits the detection to the control system that issues the bulkhead activation signal has detected a condition that has already become the catastrophic breach by the time the activation signal reaches the bulkhead. The sensor-activated bulkhead closes after the flood. PipeDream's passive hydraulic rotary gate closes during the flood. Not as a faster implementation of the same sensing and activation sequence, but as a different physical principle entirely. The gate closes because the flood physically closes it, not because any detection transmission processing activation sequence has been completed. The Venturi trigger. The passive hydraulic rotary gate's trigger is the Venturi effect, the pressure reduction that occurs in a constriction through which fluid is flowing at high velocity. The gate mechanism's design exploits the Venturi effect at the junction between the intact crystal tube section and the gate's mounting geometry in a specific and elegant way. The gate is designed so that the water inrush from a breach event, flowing toward the breach through the crystal tube's interior volume from the intact side, produces a Venturi pressure reduction at the gate's mounting position that is greater than the mechanical latch's retention force, releasing the latch and allowing the gate to close under the pressure differential that the water inrush itself produces. The gate is held open by the high-tension mechanical latch, a spring-loaded mechanism that maintains the gate in the open position against the gate's own weight and the hydraulic drag the gate's geometry produces in the normal atmospheric flow through the crystal tube. The latch's retention force is specified to maintain the gate in the open position throughout the crystal tube's full operational load range. The atmospheric management system's pressure fluctuations, the transit pod's piston effect as it passes through the gate's position, the thermal expansion and contraction cycles the tube wall material produces across the freshwater zone's temperature gradient. None of these produce the pressure differential at the gate's mounting position that releases the latch. The water inrush produces the pressure differential that releases the latch. Not any water inrush, the atmospheric management system's normal water drainage and the ballast circuit's normal flow through the utility zone are within the operational load range that the latch maintains against. The water inrush from a breach event is specifically differentiated from the operational water flows by two properties, the velocity and the volume rate. The breach event's inrush velocity is driven by the full hydrostatic pressure differential across the breach, 3 atmospheres at 30 meters depth, producing inrush velocities far above any operational flow velocity in the crystal tube's atmospheric interior. The volume rate is similarly far above operational rates. The breach geometry's cross-section multiplied by the inrush velocity produces a volume rate that the atmospheric management system cannot compensate for, which is the condition that distinguishes the breach from the operational water drainage event. At the inrush velocity that the hydrostatic pressure differential produces, the Venturi pressure reduction at the gate's mounting position exceeds the latch's retention force by the factor the gate geometry's Venturi coefficient specifies. The latch releases. The gate closes along the curved track that the gate's mounting geometry provides. The water that is flowing from the intact side toward the breach is now flowing against the closed gate. The gate's surface area, multiplied by the inrush pressure differential, produces a closing force on the gate that increases as the inrush velocity increases. The larger the breach, the higher the inrush velocity, the greater the pressure differential, the tighter the gate closes. The worst breach produces the tightest seal. The safety mechanism's closing force increases with the hazard's severity. This is not a general property of safety mechanisms, it is the specific property of the passive hydraulic rotary gate's design, produced by the physics of the Venturi effect at the gate's mounting geometry in the breach inrush flow field. The safety mechanism is not fighting the hazard. The safety mechanism is using the hazard's physics to close the gate that isolates the hazard. This is safety engineering at its most formally elegant. The hazard's physical mechanism is the safety response's activation mechanism. The breach causes the inrush. The inrush closes the gate. The gate isolates the breach. The isolation prevents the cascade. The cascade's prevention is the safety system's objective. The hazard's physics produce the safety system's response without any detection, transmission, processing, or actuation latency. The response time is 0. The gate closes as the inrush begins, faster than any sensor-activated alternative, because the response is not activated by detection of the hazard. The response is activated by the hazard itself. The gate's material and geometry. The passive hydraulic rotary gate's primary structural material is titanium aluminide, a TL intermetallic compound that provides the combination of high specific stiffness, high temperature resistance, and corrosion resistance in the cenote water's calcium bicarbonate chemistry that the gate's structural specification requires. Titanium aluminide selection over the more widely available marine engineering structural materials is specific to the gate's design constraints. The gate must be light enough that the latch's specified retention force can hold it open without the latch mechanism becoming oversized. A larger latch requires a larger Venturi pressure reduction to release it, which requires a higher inrush velocity to produce, which means a smaller or slower developing breach might not produce sufficient Venturi pressure reduction to release the gate. The gate's mass is an operational parameter of the safety mechanism, not merely a weight reduction objective. Titanium aluminide's density, approximately half that of stainless steel at equivalent strength, allows the gate's mass to be maintained within the range that the Venturi release trigger's design specifies without the gate's cross-section and surface area being reduced below the minimum that the hydraulic seal's integrity requires. The gate's geometry, the curved track that the gate closes along, is specified by the hydraulic seal requirement. A flat gate closing against a flat seat produces a seal whose quality depends on the surface flatness of both the gate and the seat, and on the evenness of the closing force distributed across the seal's full perimeter. Surface flatness deviations and closing force distribution non-uniformity produce local seal gaps, points in the seal perimeter where the gate is not fully seated against the seat, through which the pressurized cenote water leaks at a rate the pressure differential determines. The curved track converts the flat gate's closing motion into a rotational closing motion. The gate rotates about the hinge axis as it closes, with the gate's sealing surface tracing a curved path in three-dimensional space that produces a wiping action at the seal interface as the gate approaches the closed position. The wiping action removes debris, limestone particulate from the collar failures, fracture fragments, biological material from the synthetic reef community's surface disruption, any solid material that the inrush has carried from the upstream side, from the seal interface before the gate reaches the fully closed position. A flat gate closing against a contaminated seal surface closes with debris between the gate and the seat. The curved track's wiping action closes with the debris swept to the seal periphery, where it is excluded from the primary seal by the gate's edge geometry. The high-diameter rubberized seal that lines the gate's seating surface provides the compliance that the seal's leakage specification requires, not a rigid metal-to-metal contact that depends on surface flatness for its seal quality, but a compliant elastomeric surface that deforms around the surface irregularities of the gate's seating surface and the irregularities of any residual debris that the wiping action did not fully exclude. The high diameter, the high shore hardness specification that characterizes this rubberized seal relative to softer elastomeric materials, provides the compliance at the microscale while maintaining the stiffness at the macroscale that the pressure differential's load requires. The pressure differential's load on the closed gate is the closing force's source, the cenote water at the breech depth, pressing against the gate's area at the hydrostatic pressure the depth produces, creates the force that seals the gate against the seat. Higher pressure, deeper depth, larger breech, produces higher closing force, higher sealing quality, lower leakage rate. The gate is sealed by the pressure that would penetrate if the gate were not sealed. The hazard provides the safety mechanism's closing force as well as its activation energy. The complete passive safety response is therefore driven entirely by the hazard's physical conditions. The breech's inrush velocity activates the gate through the Venturi trigger. The breech's hydrostatic pressure seals the gate through the closing force. No external energy. No control signal. No sensor. No latency. The breech closes the gate the moment the breach occurs. The supercapacitor secondary protocol. The passive hydraulic rotary gate's closure isolates the breech hydraulically. Water cannot flow from the cenote through the breech into the intact crystal tube sections on the gate's protected side. But the transit pod in the crystal tube section approaching the closed gate at the boulevard's operating speed is not hydraulically isolated by the gate's closure. The pod is a solid object traveling at a velocity that carries significant kinetic energy, the product of the pod's mass and the square of its velocity, that the gate's hydraulic closure does not arrest. A pod approaching a closed gate at boulevard speed and contacting the gate at boulevard speed produces an impact whose kinetic energy is the pod's mass multiplied by the square of the boulevard speed. The gate's titanium aluminide structure is specified to absorb this impact without structural failure. The gate is the impact barrier, and the gate's structural specification includes the pod impact load alongside the hydrostatic seal load as a simultaneous design requirement. But the pod impact at boulevard speed produces deceleration forces on the pod's occupants that the coordinating system's passenger safety specification does not permit. The impact decelerates the pod from boulevard speed to zero in the pod's contact time with the gate, producing occupant deceleration far above the human body's tolerance for impact. The supercapacitor magnetic braking protocol addresses this. When the passive hydraulic rotary gate closes, the supercapacitor banks embedded in the cave walls adjacent to the gate's position discharge into the maglev induction track in the crystal tube sections upstream of the closed gate, reversing the maglev polarity that the normal electromagnetic transit uses for propulsion. The reversed polarity applies a braking force to the transit pod's Halbach array magnets, a magnetic braking force in the direction opposite to the pod's travel, decelerating the pod at a rate the supercapacitor bank's discharge current determines. The supercapacitor bank's discharge current is specified to produce pod deceleration within the human body's impact tolerance limit, the maximum deceleration rate that the seated occupant in the pod's restraint system can sustain without injury. The deceleration rate is matched to the pod's distance from the closed gate at the moment of gate closure. A pod close to the gate when the gate closes has shorter deceleration distance and requires higher deceleration force. A pod distant from the gate when the gate closes has longer deceleration distance and can be decelerated at lower force over the longer distance. The supercapacitor discharge profile is shaped by the gate's closure event's timing and the pod's position monitoring. The coordinating system's transit management layer provides the pod's position at the gate closure moment to the supercapacitor discharge control logic, which shapes the discharge profile to produce the deceleration force appropriate for the available deceleration distance. The supercapacitor power source is the critical element of the secondary protocol's reliability. The supercapacitor banks are charged from the streaming potential harvest system's power output, which is continuous as long as the underground river flows. The supercapacitor banks maintain their charge state regardless of the crystal tube network's electrical system status. The blackout protocol's power failure that eliminates the electromagnetic propulsion system does not eliminate the supercapacitor bank's charge, because the streaming potential harvest is not the electromagnetic propulsion system's power source and is not interrupted by the same failure conditions. The supercapacitor's specific advantage over battery energy storage in this application is the discharge rate. A supercapacitor can discharge its stored energy at the current rate that the magnetic braking load demands, a rate that a battery's internal resistance would limit below the braking force the deceleration specification requires. The supercapacitor delivers the braking current at the rate the magnetic braking requires, not at the rate the energy storage medium's internal resistance permits. The deceleration that the supercapacitor magnetic braking protocol produces brings the transit pod to rest millimeters from the closed gate, not stopped far upstream where the deceleration began, but decelerated continuously from the moment the gate closed to a final rest position at the gate's contact point. The occupants in the pod's restraint systems have experienced a firm deceleration event, more forceful than the standard boulevard deceleration from operational speed to stop, but within the human body's tolerance limit. They are stationary. The gate is closed ahead of them. The breech is on the gate's other side. The gate's position in the network. The passive hydraulic rotary gate is positioned at every crystal tube junction with a hub, at every intersynode corridor's entry point at each synote's boundary, and at every crystal tube section's segment boundary where the DSI principles analysis determines that isolation at that boundary provides the highest network integrity protection for the current section's failure scenarios. The hub junction gate position is the gate's most frequent deployment location and its most consequential. The hub is the crystal tube network's most operationally significant node, concentrating the transit, utility, atmospheric management, and habitation functions that the crystal tube standard provides in a single architectural structure. A breach event in a crystal tube section connecting to the hub, without a gate between the section and the hub, propagates the breach into the hub's full atmospheric volume, a volume many times larger than the crystal tube section's volume, whose loss of atmospheric integrity would be an evacuation event of far greater magnitude than the crystal tube section's isolated loss. The gate between the crystal tube section and the hub prevents the crystal tube section's breach from reaching the hub. Not by preventing the breach, the gate closes after the breach has occurred. By preventing the breach's propagation into the hub's atmospheric volume, which the closed gate seal achieves by stopping the water inrush before it reaches the hub junction. The hub's atmospheric volume is on the gate's protected side. The crystal tube section is on the gate's unprotected side. The gate's closure preserves the hub's atmospheric integrity regardless of the crystal tube section's breach extent. The intersynode corridor entry gate is the regional network's most geopolitically significant gate position, the gate that separates the corridor synote's freshwater zone from the intersynode crystal tube passage through which the crystal tube connection runs. A failure in the intersynode passage, a sealing collapse in the limestone between synotes, a dissolution event that severs the intersynode passage's structural integrity, would, without the entry gate, admit the synote water into the intersynode passage's atmospheric interior and propagate the hydraulic event toward both synotes at each end of the passage. The intersynode passage entry gates at both synotes close simultaneously when either gate's Venturi trigger detects the breach inrush. The simultaneous closure isolates the intersynode passage from both synotes' atmospheric interiors, preserving both synotes' atmospheric integrity and limiting the hydraulic event to the intersynode passage's interior volume, which contains no inhabited space, no longevity program infrastructure, and no visitor program activity by the safety protocol's operational separation requirement. The intersynode passage is occupied by maintenance subs on scheduled transits, and the maintenance sub's emergency protocol in a passage breach event is the Avalo system's deployment, the mechanical drive's engagement, and the progression toward the nearest wetlock at the passage's synote end, the end whose gate has closed on the synote side, which the wetlock's docking protocol can still accommodate because the wetlock's access is from the crystal tube network's interior, not from the intersynode passage's exterior. The gate's maintenance cycle. The passive hydraulic rotary gate is a mechanical system. Mechanical systems accumulate wear. The gate's latch mechanism, the spring-loaded retention system whose release produces the gate's closure, is the gate's highest wear component. The latch spring is in sustained tension throughout the gate's open operational period, and sustained tension is the failure mode that springs accumulate damage toward. The latch spring service life under sustained tension is the gate's primary maintenance scheduling parameter. The gate's maintenance cycle is the latch spring's replacement cycle, scheduled by the coordinating system's condition monitoring based on the spring's operational period since last replacement and the acoustic characterization data that the coordinating system's gate monitoring protocol collects during each gate inspection. The inspection is performed by the maintenance sub's gate inspection protocol, a systematic acoustic characterization of the gate's latch mechanism, hinge assembly, and sealing surface that the maintenance sub executes on the gate inspection schedule the coordinating system specifies for each gate in the network. The latch spring's acoustic characterization provides the condition indicator that the condition-based maintenance model requires. The spring's acoustic resonance frequency under the applied tension changes as the spring's microstructure accumulates fatigue damage, shifting measurably from the fresh spring's baseline resonance frequency toward the failure fatigue frequency that the spring material's characterization data specifies. The shift rate, the rate at which the resonance frequency moves from the baseline toward the failure fatigue frequency, is the condition indicator slope. The condition indicator's absolute value is the current fatigue damage accumulations fraction of the total fatigue life the spring's material specification allows. The spring replacement is scheduled when the condition indicator reaches the threshold the coordinating system's gate maintenance protocol specifies, the fatigue damage accumulation fraction above which the remaining service life is below the safety margin the protocol requires. The replacement is performed by the maintenance sub-standard cartridge swappable procedure. The latch spring is a cartridge format component, accessible from the gate's maintenance access panel, replaceable by one maintenance technician with standard tools in the gate's installation aisle. The replacement restores the condition indicator to the baseline. The monitoring resumes from baseline. The gate sealing surface, the high diameter rubberized seal that the gate's geometry produces the wiping contact with at closure, accumulates compression set damage from each closure event. Compression set is the permanent deformation that a rubberized material accumulates when compressed beyond the elastic recovery threshold for sufficient time, the relaxation of the rubber's internal cross-linking structure under sustained compression that produces a permanent reduction in the material's thickness and therefore in the seal's ability to achieve the intimate surface contact that its leakage specification requires. Each gate closure event compresses the seal for the duration of the breach event's management, the interval from the gate's closure to the Terraform operator's authorized restoration of the gate to the open position after the breach's repair and the biological monitoring's confirmation of recovery. This interval ranges from hours for minor breach events to days for major ones. The compression set damage accumulated in each closure event is not recovered when the gate opens, it is permanent. The seal's cumulative compression set is the seal's service life consumption. The seal's replacement is scheduled when the cumulative compression set exceeds the leakage specification's allowance. The seal replacement schedule is not primarily driven by the gate's closure event frequency. In the normal operations of a well-managed formation cenote installation, major breach events requiring gate closure are infrequent, and the seal's compression set accumulation rate from the infrequent closure events is below the replacement threshold across the typical gate replacement cycle. The seal replacement is primarily driven by the cyclic compression that the transit pod's piston effect produces. Each pod transit past the gate position compresses the atmospheric air ahead of the pod, producing a brief positive pressure pulse followed by a brief negative pressure pulse at the gate's sealing surface. These cyclic pressure pulses, at the frequency the transit schedule produces across the full design life, produce cyclic strain in the seal's elastomeric material that accumulates as fatigue damage in the same way the latch spring's sustained tension accumulates fatigue damage. The coordinating system's gate maintenance protocol models both damage mechanisms simultaneously, the closure event compression set and the piston effect fatigue, and schedules the seal replacement when the combined damage reaches the leakage specification's threshold. The combined damage model is more accurate than either mechanism modeled alone, because the two mechanisms are not independent. A seal that has accumulated significant piston effect fatigue is more susceptible to permanent deformation from the closure event compression set than a fresh seal. The combined model's interaction term captures this. The fatigue damage's contribution to the compression set susceptibility is explicitly modeled, producing a more conservative replacement schedule for seals in high transit frequency gate positions than the simple additive combination of the two damage rates would produce. The seal replacement schedule is more conservative in high transit frequency positions. The safety margin is maintained in the positions where the traffic load is highest. The maintenance investment is allocated to the safety risk rather than distributed uniformly across all gate positions regardless of their specific loading history. Double gate configuration. The passages connecting the formation cenote's inhabited zones to the deep gallery's compute infrastructure, the passages that cross the halocline boundary and enter the saltwater zone where the chemostat zone's hydrogen sulfide chemistry begins, carry a doubled gate configuration at the zone boundary crossing. Two passive hydraulic rotary gates in series, separated by the intermediate isolation chamber between them. The double gate configuration addresses the specific failure scenario that the single gate cannot adequately manage at the zone boundary crossing, the gradual seal degradation that the halocline zone's chemistry produces in the gate's sealing surface material. The halocline boundary's chemistry, the transition from the freshwater zone's calcium bicarbonate chemistry to the saltwater zone's elevated chloride and the early H2S detection concentrations, is more chemically aggressive to elastomeric materials than either zone alone. The high durometer rubber's cross-linking chemistry is attacked by the halocline's specific combination of salinity, pH transition, and early H2S exposure at a rate that the freshwater zone's gate sealing surfaces do not experience. A single gate at the halocline zone crossing with a chemically attacked seal provides less seal integrity than the maintenance protocol's replacement cycle would ensure. The double gate configuration's intermediate isolation chamber provides the safety factor. The outer gate, facing the saltwater zone, is subject to the full halocline chemistry attack on its sealing surface, and is replaced at the more frequent schedule that the halocline chemistry's degradation rate requires. The inner gate, facing the freshwater zone, is in the freshwater chemistry that the standard maintenance schedule addresses. If the outer gate seal has degraded below specification before its scheduled replacement, the inner gate provides the independent isolation that maintains the network's DSI integrity. The intermediate isolation chamber between the two gates is inspected at every maintenance cycle. The chamber's atmospheric condition, structural integrity, and any chemical contamination that has penetrated the outer gate's degraded seal are assessed before the inner gate is opened for access to the compute infrastructure beyond. The inspection ensures that the inner gate is not opened into a chamber that the outer gate's degraded seal has allowed halocline chemistry to contaminate. The inspection is the operational safety protocol that the double gate configuration structural safety provision requires for its full protection to be realized. The double gate configuration's inspection requirement is the cartridge swappable principle applied to the safety architecture. The inner gate cannot be opened without the intermediate chamber's inspection, and the inspection cannot proceed without the maintenance sub's protocol execution. The protocol execution requires the maintenance sub's passage through the outer gate. The outer gate opens for the maintenance sub's entry, and the outer gate's opening for maintenance is the same opening that would allow halocline chemistry intrusion if the outer gate's seal has failed. The outer gate's scheduled replacement, at the more frequent halocline chemistry degradation rate, must be current before the maintenance sub can safely enter the intermediate chamber. The maintenance schedule, the inspection protocol, and the replacement frequency are all constitutionally protected within the Redeemer Governance Framework's infrastructure maintenance standards for safety-critical components. The outer gate's replacement cannot be deferred beyond its scheduled date by the economic accounting function's cost optimization, by the transit management layer's scheduling constraints, or by any other operational consideration. The replacement date is the safety architecture's commitment to the formation's conditions. The conditions determine the schedule. The schedule determines the operation. The gate in the blackout protocol. The passive hydraulic rotary gate's passive trigger, the Venturi effect in the breech inrush flow, activates in the blackout protocol's power failure condition exactly as it activates in normal operation, because the Venturi trigger requires no power. The water flowing through the gate's mounting geometry produces the pressure differential. The pressure differential releases the latch. The gate closes. No power required at any step. The supercapacitor magnetic braking protocol's power source, the supercapacitor banks charged from the streaming potential harvest, is not affected by the blackout protocol's power failure condition, because the streaming potential harvest is not part of the crystal tube network's electrical system that the blackout protocol's failure condition interrupts. The streaming potential harvest is a separate electrical circuit that continues generating current from the underground river's flow regardless of the crystal tube network's electrical status. The supercapacitor banks remain charged. The magnetic braking protocol remains available. The combination, passive Venturi gate activation and supercapacitor magnetic braking, produces the complete gate response in the blackout protocol's power failure condition with the same effectiveness as in normal operation. The safety architecture is power independent. The failure that eliminates power does not eliminate the safety response to breaches that occur under power failure conditions. This property was not designed as a blackout safety provision. It is the consequence of designing the gate's activation and the braking protocol's power source both around the principle that safety responses should derive from the physics of the hazard they respond to rather than from the electrical power that the hazard might eliminate. A safety response that depends on the power that the hazard eliminates is a safety response whose effectiveness is inversely correlated with the hazard's severity. The passive hydraulic rotary gates and the supercapacitor's design independence from the network's electrical power are both consequences of the same design principle. The safety response's activation mechanism must not be the same system the hazard attacks. The blackout protocol's power failure is a hazard. The crystal tube network's electrical systems are the system the blackout protocol attacks. The gate's Venturi trigger and the supercapacitor's streaming potential harvest are not the crystal tube network's electrical systems. They are independent of what the blackout protocol attacks. The safety architecture is independent of the hazard it protects against in both the breach event and the blackout protocol's power failure scenarios. What the gate never does. The passive hydraulic rotary gate never fails to close when the Venturi trigger activates. This is the claim the safety architecture requires and that the gate's design must support across the design life. Not a performance target. A constitutional specification, the gate closes when the Venturi trigger produces the pressure differential that releases the latch, under all conditions within the gate's design envelope, without exception. The gate's design envelope includes the full range of inrush velocities from the minimum breach geometry at the maximum depth zone's hydrostatic pressure differential to the maximum breach geometry at any depth zone's hydrostatic pressure differential. Within this envelope, the Venturi trigger's pressure differential is always above the latch's retention force. The design margin between the minimum trigger pressure differential and the maximum latch retention force is specified in the gate's dimensional and material specification as the primary safety margin, dimensioned to provide the certainty that no combination of manufacturing variants within the tolerance specification and latch were within the maintenance replacement schedule produces a gate that fails to release. The design envelope excludes conditions where the inrush velocity is too low to produce the minimum Venturi trigger pressure differential, specifically, the very slow, very small breach that admits water at a rate below the minimum inrush velocity. This condition is not a gate failure. It is a condition outside the gate's design envelope, a breach so slow that the atmospheric management system's pressure supply can compensate for the inflow without the atmospheric pressure declining to the level that produces the minimum inrush velocity. This condition is the slow leak, a microbreach that produces gradual atmospheric pressure decline rather than the rapid inrush that the Venturi trigger responds to. The slow leaks management is the Crystal Tube Standards pressure monitoring protocol's responsibility, not the gate's responsibility. The pressure monitoring detects the gradual pressure decline, identifies the breach through the differential pressure analysis between adjacent crystal tube sections, and notifies the Terraform operator through the standard monitoring alert pathway. The Terraform operator's response is the maintenance sub's deployment to locate and seal the microbreach, a repair operation rather than an emergency isolation event. The gate is not involved because the gate's design envelope excludes the slow leak's inrush velocity. The clarity about what the gate never does, fails to close within its design envelope, and what the gate does not do, close in response to conditions outside its design envelope, is the safety architecture's honest representation of the gate's function and limits. The gate closes the conditions it was designed to close. The pressure monitoring and the Terraform operator's repair protocol manage the conditions the gate was not designed to close. A safety system that claims to close all conditions is a safety system whose claim is false and whose false claim is the basis for false confidence. Pipedream's safety architecture claims only what the design can deliver. The gate closes within its design envelope. The pressure monitoring manages outside the design envelope. Together they cover the full threat space. Neither alone covers the full threat space, and neither claims to. The honesty about what each component does and does not do is the safety architecture's most important property, and the one that the founding charter's governance architecture most directly protects. The digital twin's record of gate performance, the Terraform operator's breach event assessment, the maintenance protocol's gate condition monitoring, all of these are the evidence base that the safety architecture's honesty about its performance rests on. The REDEEM framework's constitutional protection of this evidence base prevents the reclassification of gate performance data that would produce false confidence in a gate specification that is not performing to its design envelope. The gate never fails to close within its design envelope. The digital twin records every gate closure event and every gate condition monitoring result. The record is the evidence. The evidence is the Constitution's protection. The protection is what makes the claim. The gate never fails to close within its design envelope, a true claim rather than a marketing claim. The gate is civilizational commitment. The passive hydraulic rotary gate is a commitment expressed in titanium aluminide and rubberized elastomer, the commitment that when the formation produces a breach event, and the formation will produce breach events across the 1,000-year design life, because geological systems operating on geological timescales produce formation events at geological frequencies, the civilization's safety architecture responds without latency, without power dependency, without sensor requirement, using only the physics of the breach event itself to produce the isolation that prevents cascade. This commitment is the safety architecture's expression of the aquaforming doctrine at the structural level. The formation is allowed to be the formation. The formation's geological events are not prevented. They are accommodated. The breach event is accommodated by the gate that closes when the breach event's physics produce the Venturi trigger. The accommodation is fast, complete, and independent of any infrastructure that the breach event might also have disabled. The surface world safety engineering accommodates the formation's geological events through redundancy, multiple systems each designed to prevent the event, with the understanding that if one system fails the others maintain the prevention. The redundancy multiplies the systems. Each additional system is additional infrastructure that the formation's geological conditions can also affect. Pipedream's passive hydraulic rotary gate accommodates the formation's geological events through simplicity, one mechanism, activated by the event's own physics, requiring no infrastructure beyond the mechanism's own mechanical function. The simplicity is not a concession to resource constraints. It is the correct engineering response to the insight that a safety system that uses the hazard's physics as its activation mechanism cannot be disabled by the hazard. The fewer the components between the hazard's physics and the safety response, the more certain the response. The gate closes. The breach is isolated. The formation has produced what it produces. The civilization continues operating in the sections the gate has protected. The Terraform operator assesses the breach. The coordinating system monitors the biological recovery. The restoration is authorized when the assessment confirms recovery. The gate opens. The network resumes. The formation produced the event. The civilization accommodated the event. The formation and the civilization are still cohabiting. The gate made the cohabitation survive the event. The gate's relationship to the caller. The caller and the gate are the safety architecture's complementary provisions, the caller addressing the kinetic propagation phase, the gate addressing the hydraulic intrusion phase. Their relationship is sequential. The caller fails first, kinetically decoupling the affected section from the adjacent sections. The gate closes second, hydraulically isolating the breach from the intact network. The timing relationship between the caller failure and the gate closure is the safety architecture's most precisely designed temporal parameter. The collar failure's acoustic signature arrives at the gate's monitoring position, the acoustic transceiver node adjacent to the gate's installation, before the inrush reaches the gate's mounting geometry, because the acoustic signal propagates at acoustic velocity in the cenote water while the inrush propagates at hydraulic velocity. The hydrostatic pressure differential drives the water column at the tube's cross-section. The acoustic velocity is faster than the hydraulic velocity. The supercapacitor magnetic braking protocol's activation is triggered by the collar failure's acoustic signature, not by the gate's closure event. The acoustic monitoring's detection of the collar failure, faster than the hydraulic inrush's arrival at the gate, activates the supercapacitor discharge that begins decelerating the transit pod before the gate closes. By the time the gate closes, the pod's deceleration has been underway for the time interval between the acoustic signal's arrival at the monitoring position and the hydraulic inrush's arrival at the gate. The pod is slower when the gate closes than it was when the collar failed. The pod's remaining velocity at gate closure is lower than its velocity at collar failure. The supercapacitor braking protocol achieves progressive deceleration that reduces the pod's impact velocity on the gate to the level the safety specification requires. The sequential design, collar, acoustic detection, supercapacitor braking initiation, gate closure, produces a safety response whose components are temporally coordinated not by a control system but by the physics of the event's propagation at different velocities through different media. The collar's acoustic signal travels faster than the inrush. The inrush closes the gate. The acoustic signal's arrival before the gate closure initiates the braking before the gate closes. The physics of acoustic versus hydraulic propagation produces the temporal coordination that the safety specification requires. No control system coordinates the sequence. The physics coordinates the sequence. The safety architecture uses the physics. Cross-references, Part 2, CH4, The Crystal Tube Standard, Part 7, CH1, Breakaway Architecture, Part 7, CH3, Compartmentalized Cities, Part 7, CH4, Living Through Failure, Part 7, CH5, The Blackout Protocol, Part 10, CH2, Electrochemical Harvest. For passive hydraulic rotary gate material specification and Venturi trigger geometry dimensioning protocol, see Appendix D, Construction Operations Manual. For latch spring condition monitoring acoustic resonance protocol and seal compression set damage model, see Appendix D, Construction Operations Manual. For double gate configuration halocline zone intermediate chamber inspection protocol, see Appendix D, Construction Operations Manual. For supercapacitor discharge profile specification and transit pod position integration protocol, see Appendix D, Construction Operations Manual. For gate maintenance schedule constitutional protection and economic accounting override prohibition, see Appendix H, Governance Operations Manual. Pipe dream. Part 7, Safety First. Chapter 3, Compartmentalized Cities. The city is the surface world's most complex safety engineering challenge and its least systematically addressed. The surface world cities have fire departments and building codes and seismic zones and flood maps and emergency services and redundant utilities and evacuation routes. All of these are safety provisions, each addressing a specific hazard class, each designed and maintained by a specific institutional authority, each funded by a specific budget line that competes annually with every other budget line the municipal governance structure manages. What the surface world cities do not have is a coherent safety architecture, a single design framework that specifies how all of the individual safety provisions relate to each other, how they interact when multiple hazard classes manifest simultaneously, and how the city's spatial organization reflects the safety architecture's requirements rather than the real estate market's optimization of land value. The fire department's provision is independent of the seismic zone designation, which is independent of the flood map's evacuation route specification, which is independent of the building code's structural requirement. Each provision addresses its specific hazard in isolation from the others. The city that experiences a simultaneous seismic event and building fire during a flood event discovers the gap between independent safety provisions designed for individual hazard classes and an integrated safety architecture designed for the city's full hazard space. Pipe dream is not a city in the surface world sense. It is a pressurized underground installation in a geological system that produces geological events. But pipe dream is a city in the functional sense. It has residential zones, commercial zones, research zones, governance zones, transit infrastructure, utility infrastructure, and a population whose safety across the full hazard space requires more than the individual safety provisions for individual hazard classes that Chapter 1's breakaway architecture and Chapter 2's automatic bulkheads address. Compartmentalized cities are pipe dream's architectural response to the gap between individual safety provisions and a coherent safety architecture. The spatial organization of the cenote installation's functional zones to reflect the safety architecture's requirements rather than purely the operational efficiency criteria that would organize the zones if safety considerations were addressed only through individual provisions. The compartment concept. A compartment in the pipe dream safety architecture is a spatial zone whose atmospheric integrity can be maintained independently of every other zone's atmospheric integrity, simultaneously with every other zone's atmospheric integrity, for the duration of any single formation event or combination of formation events that the geological model specifies as within the design envelope. The compartment is not the crystal tube section. The crystal tube section is the network's minimum structural element, whose DSI isolation through the collar and gate mechanisms Chapter 1 and Chapter 2 document. The compartment is the aggregation of crystal tube sections and connected atmospheric volumes that forms a functionally coherent unit: the residential zone, the transit hub, the deep gallery research installation, the aquaculture cities production galleries, within which the coordinating system maintains common atmospheric management, common biological monitoring, common visitor access management, and common governance authority. The compartment's atmospheric isolation is its defining safety property. The compartment can be isolated from all adjacent compartments simultaneously by the gate mechanism's closure at every boundary between the compartment's crystal tube sections and the adjacent compartment's crystal tube sections. The isolation is complete, no atmospheric communication between the isolated compartment and the adjacent compartments through any path that the safety architecture specification has not controlled. The isolation is achievable by the gate mechanism's passive response to the formation event's physics, without requiring coordinating system intervention, without requiring power supply beyond the supercapacitor bank's available charge, and without requiring any human action in the compartment during the event. The compartment's functional coherence is its operational definition. Within the compartment's boundaries, the residential and operational functions that the compartment hosts can be sustained for the duration that the compartment's atmospheric management system's resources, the nitrox supply, the CO2 scrubbing capacity, the thermal management capacity, can provide, without any external supply from the adjacent compartments. The duration is the compartment's self-sufficiency period, the time the isolated compartment can sustain its occupied population at the atmospheric specification the functional zone requires. The self-sufficiency period is the design parameter that links the safety architecture's isolation capability to the operational consequence of isolation. An isolated compartment that can sustain its population for 4 hours provides a different safety outcome than one that sustains for 48 hours. 4 hours is enough for the Terraform operator's breach event assessment to confirm the breach's extent and initiate the repair protocol. 48 hours is enough for the breach's repair to be completed and the isolation to be lifted before the compartment's resources are exhausted. The self-sufficiency period is specified for each compartment type as the maximum estimated duration of the breach event's full management cycle, assessment plus repair plus coordinating system verification of restoration, with the safety factor the founding charter's life safety specification requires. The residential zone's compartment design. The residential zone's compartment design is the safety architecture's most consequential application because the residential zone is the installation's highest vulnerability occupancy type: sleeping residents whose awareness of a formation event may be delayed by sleep, whose mobility through the zone is constrained by the accommodation section's geometry, and whose atmospheric resource consumption includes the sleep phase reduced metabolic rate that the atmospheric management protocol monitors but that the design basis emergency assumes cannot be relied on because the emergency's stress response elevates the metabolic rate regardless of the pre-event sleep phase. The residential zone self-sufficiency period is specified at the maximum estimated full management cycle duration, 72 hours, with the additional safety factor that the founding charter's life safety specification requires for the occupancy type with the lowest average mobility. 72 hours multiplied by the full occupancy population's atmospheric resource consumption rate at the elevated metabolic rate the emergency stress response produces determines the compartment's atmospheric management system's resource inventory requirement. The atmospheric management system's resource inventory for a residential zone compartment at full occupancy for 72 hours at elevated metabolic rate is substantial. The nitrox supply cylinder banks that occupy the residential zone's utility access panels, the CO2 scrubbing material cartridges staged in the compartment's maintenance access area, and the thermal management system's fluid reservoir that maintains the variable conductivity suit protocol during the isolation period. Each resource has its own inventory specification derived from the 72-hour full occupancy elevated metabolic rate calculation, with the safety factor applied to each independently. The independence of the resource inventory calculations is a deliberate design decision. The atmospheric management system's resource shortage in a single component, the CO2 scrubbing material's early exhaustion, for example, should not produce atmospheric failure while the nitrox supply remains abundant. Each component's inventory is independently sufficient for the full 72-hour period. The compartment does not run out of any resource before any other resource. The simultaneous resource sufficiency is the design target. The communal gallery's compartment boundaries, the gates that separate the communal gallery from the individual accommodation sections, are positioned to allow the communal gallery to be isolated from the individual accommodation sections independently. This configuration produces a safety architecture that can respond to a breach in the communal gallery by isolating the communal gallery from the accommodation sections, preserving the accommodation section's atmospheric integrity while the communal gallery breach is managed. Or it can respond to a breach in an individual accommodation section by isolating that section from the communal gallery, preserving the communal gallery's atmospheric integrity and allowing the residential zone's remaining population to gather in the communal gallery during the breach management period. The compartment boundary configuration's flexibility is the residential zone's most important safety property. The gates can be closed in any combination that the breach event's location requires, producing the smallest isolated region that contains the breach while preserving the largest possible volume of intact atmospheric enclosure for the residential zone's population. The compartment does not isolate the entire residential zone in response to a single accommodation section's breach. It isolates the affected section. The compartment boundaries that allow this granular isolation are the crystal tube standards gate positions at every junction in the residential zone's crystal tube network, not just at the zone's external boundaries with adjacent compartment types, but at the junctions within the residential zone between the accommodation sections, the communal gallery, and the utility access corridors. Every junction is gated. Every gate can be independently closed by the Venturi trigger's passive response. The granular isolation the safety architecture achieves is the product of the granular gate placement that the crystal tube standards design philosophy produces throughout the residential zone. The transit hub's compartment design. The transit hub is the installation's highest throughput atmospheric volume, the point through which all visitor transit enters and exits the freshwater zone's crystal tube network, all intercity transit passes, all cargo transit moves, and the full complement of the installation's daily maintenance sub-operations. The transit hub's occupancy is continuous and variable. Day visitors departing on the morning's first cycle sub-transit, safari participants returning from the overnight waypoint accommodation, maintenance crews transferring cargo from the intercity transit to the hub's processing gallery, longevity program participants moving between their accommodation sections and the communal gallery's breakfast session. The transit hub's compartment design is driven by the throughput requirements conflict with the isolation requirement. The gates that produce the compartment's isolation interrupt the throughput that the transit hub's function requires. Every gate that closes across a transit corridor eliminates that corridor's transit capability for the duration of the gate's closure. A transit hub whose compartment design produces maximum isolation capability produces minimum throughput during formation events. A transit hub whose compartment design produces maximum throughput during formation events produces minimum isolation capability. The design resolution is operational priority ordering. The transit hub's gates are organized in priority tiers, with the highest priority gates, the gates that isolate the hub from the intercity crystal tube passages and from the deep gallery infrastructure below the hub, positioned and specified for the fastest and most reliable closure, and the lower priority gates, the gates between the hub's internal functional zones, specified for reliable closure within a longer activation window. That the higher priority gates closure has bought by isolating the highest risk breach scenarios first. The priority ordering reflects the consequence analysis. A breach in the intercity crystal tube passage that connects the transit hub to the adjacent cenote is the highest consequence breach scenario for the transit hub, because the intercity passage has no habitation population to protect and can be isolated without affecting the hub's full population, while a breach in the hub's internal zones involves the hub's full occupancy population and requires the most granular isolation. Capability. The highest priority gates isolate the no occupancy scenarios. The lower priority gates manage the occupancy scenarios within the time the highest priority gates isolation has bought. The transit hub self-sufficiency period specification is shorter than the residential zones, 48 hours, reflecting the transit hub's higher average occupancy mobility. Transit hub occupants are by definition mobile enough to be in the transit hub, and the coordinating system's evacuation management protocol can direct the hub's population to the adjacent residential zones through the crystal tube network's maintained sections within the evacuation time. The operational assessment specifies. The evacuation reduces the hub's occupancy population during the breach event management period, reducing the resource consumption rate that the self-sufficiency period calculation is based on. The evacuation management protocol is the transit hub's primary safety response for breach events, not the compartment's isolation in place, but the coordinating system's direction of the hub's mobile population toward the residential zones through the transit network's intact sections before the hub's self-sufficiency resources approach exhaustion. The compartment isolation provides the time for the evacuation. The evacuation reduces the resource requirement. The resource requirement reduction extends the effective self-sufficiency period beyond the 48-hour specification. The design is correct. The deep gallery's compartment design. The deep gallery, the compute infrastructure zone, the chemostat management zone, the research accommodation zone, is the installation's most structurally isolated compartment by the formation's geology. The depth that places the deep gallery below the halocline boundary also places it below the hydrostatic conditions that the shallow formation events primarily affect. The geological events that produce collar failures and breach scenarios in the freshwater zone crystal tube sections are surface zone events. The dissolution processes and microseismic activity that the Chicxulub fracture network produces are concentrated in the fracture zones where the dissolution has produced the passage geometry the crystal tube network inhabits, which is primarily the freshwater zone's depth range. The deep gallery's geological risk profile is different. The H2S chemistry at depth is the primary chemical hazard. and the high hydrostatic pressure is the primary structural hazard, and the combination of H2S chemistry and high hydrostatic pressure at depth produces structural failure modes that are different in character from the shallow zone's dissolution and microseismic events. The deep galleries compartment design addresses these depth-specific hazards through provisions that are different in kind from the shallow zone's collar and gate architecture. The primary deep gallery safety provision is the gallery segmentation, the division of the deep gallery's total atmospheric volume into segments whose boundaries are the double gate configurations at the zone boundary crossings that Chapter 2 documented. Each gallery segment is a compartment, a volume whose atmospheric integrity can be independently maintained through the double gate configuration's inner gate, regardless of the outer gate's exposure to the halocline chemistry and the breach scenario in the intermediate isolation chamber. The gallery segmentation's segment dimensions are specified by the H2S hazards management requirement. A deep gallery segment whose atmospheric volume is breached by an H2S intrusion from the anoxic zone's management boundary can produce atmospheric H2S concentrations that are immediately dangerous to life in a volume sized to the maximum breach rate at the maximum hydrostatic pressure differential across the management boundary. The segment's atmospheric volume must be small enough that the H2S intrusion rate from the maximum breach scenario produces concentrations below the immediately dangerous concentration within the self-sufficiency period that the evacuation protocol requires. The deep gallery's self-sufficiency period specification is not based on atmospheric resource inventory alone. The deep gallery's pressurized atmospheric enclosures resources are substantial, and the permanent resident population is small relative to the transit hub's variable occupancy. The self-sufficiency period is based on the H2S intrusion management. The segment must maintain atmospheric H2S concentrations below the immediately dangerous threshold for the duration of the evacuation protocol from the deepest permanent resident position to the nearest wetlock on the freshwater zone side of the halocline boundary. The evacuation time from the deepest permanent resident position through the gallery segment's intact crystal tube sections, through the double gate configuration's inner gate into the intermediate isolation chamber, through the intermediate isolation chamber's inspection protocol, and through the outer gate into the saltwater zone's crystal tube sections toward the freshwater zone boundary is the design basis evacuation time. The self-sufficiency period must exceed the design basis evacuation time by the founding charter's life safety specifications required safety factor. The segment's atmospheric volume, the maximum breach rate, and the immediately dangerous H2S concentration threshold together determine the segment dimensions that produce a self-sufficiency period above the required safety factor. The deep galleries compartment design is the safety architecture's most chemically specific provision, not the kinetic isolation of the collar or the hydraulic isolation of the gate, but the chemical isolation of the gallery segmentation whose dimensions are calibrated to the H2S intrusion chemistry's rate in the specific geological conditions the anoxic zone's boundary presents. The chemistry determines the geometry. The geometry produces the safety. Compartment boundaries as social architecture. The residential zone's compartment boundaries, the transit hub's priority-ordered gates, and the deep gallery's double gate segmentation are all safety provisions, physical boundaries specified by the safety architecture's hazard analysis. They are also architectural features of the inhabited space, the gate's physical presence at the compartment boundaries, the intermediate isolation chamber's dedicated atmospheric volumes, the gate inspection protocol's required maintenance access. All of these are spatial features of the zones they protect. The spatial features that safety requires produce architectural consequences that the visitor experience's spatial design did not specify. The gate between the residential zone's communal gallery and the accommodation sections is a visual element in the communal gallery's spatial composition. The titanium aluminide gate, held open by the high-tension latch, is visible in the visual field of the communal gallery's occupants in the same way that a doorframe is visible in the visual field of a room's occupants. The gate is present. The gate is visible. The gate is the boundary's physical expression. The founding engineer's decision about the gate's visual treatment is the safety architecture's intersection with the visitor experience philosophy. The gate should be visible because the gate is what it is, a safety boundary whose presence communicates the compartment structure and the safety architecture's protection of the space. Concealing the gate behind architectural finishes that make the boundary appear seamless would produce a space that looks like it has no compartment boundary, which would communicate the absence of the safety protection that the gate provides. The visible gate communicates the protected compartment. The protected compartment communicates the safety architecture's confidence in the formation. The civilization has identified the hazards, specified the provisions, installed the boundaries, and is operating within the compartment structure that the safety architecture requires. The visible gate is the safety architecture's honest acknowledgement of what it is, a provision for an acknowledged hazard, not a concealment of the hazard's existence. The visitor who sees the gate in the communal gallery is a visitor who knows the safety architecture exists, who knows that the space they are in is protected by a specifically designed provision for the formation event that the gate is designed to manage. The visitor who does not know the gate exists, whose visual experience of the space has no visible gate because the architectural finishing has concealed it, does not know the safety architecture exists. The visitor who does not know the safety architecture exists has been given a visual representation of the space that is false. The space looks like it has no safety provision, but it has one, and the false representation is the concealment's product. The visible gate is the honest visitor experience. The concealed gate is a false one. This is not the founding engineer's primary reason for specifying the gate's visual exposure. The primary reason is the operational requirement that gate inspection requires visual access to the gate's components, and that visual access requires the gate to be in the visual field of the maintenance sub's inspection camera without obstruction from architectural finishes. But the visitor experience philosophy's commitment to honest representation of the formation's conditions and the civilization's response to those conditions produces the same specification from a different direction: be what you are, visibly. Fire, flood, and failure modes across compartments. The compartment design's multi-hazard capability is the safety architecture's most complex performance requirement. The same compartment boundary that isolates the residential zone from a breach event in the adjacent crystal tube section must also isolate the residential zone from a fire event in the communal gallery, from a chemical contamination event in the utility access corridor, and from a biological contamination event in the aquaculture gallery section that shares the residential zones. Compartment boundary. Fire in an enclosed pressurized atmospheric volume is a different hazard than the hydraulic breach that the gate's Venturi trigger manages. Fire consumes oxygen and produces CO2 and combustion products at rates that the atmospheric management system's scrubbing capacity may not be able to manage across the fire event's full duration. The fire safety provision is the fire suppression system, the halon equivalent suppression agent that the coordinating system's fire detection sensors activate within the affected zone when the optical and chemical sensors confirm a combustion event. The fire suppression system's activation and the gate's activation are coordinated in the compartment's safety protocol. The fire detection triggers the gate closure at the affected zone's boundaries simultaneously with the suppression system's activation within the affected zone. The gate closes before the combustion products can propagate to the adjacent compartments through the crystal tube network's atmospheric connections. The suppression agent extinguishes the fire within the affected zone. The gate isolation maintains the adjacent compartment's atmospheric integrity during the suppression event and the post-suppression assessment. The fire suppression agent's selection for the pressurized crystal tube environment is constrained by the same considerations that the scaphender's rebreather selection addressed. The suppression agent's safety at the therapeutic pressure range's nitrox atmosphere, at the occupant's respiratory physiology in the elevated partial pressure environment, and at the biological community's sensitivity to chemical agents in the freshwater zone's water chemistry. The halon equivalent agent that the crystal tube standard specifies for fire suppression in inhabited zones meets all three constraints: effective at oxygen-enriched atmospheres at elevated pressure, non-toxic to the human respiratory system at the suppression concentrations the fire event requires within the enclosed volume, and chemically compatible with the freshwater zone's water chemistry if the suppression agent reaches the water column through a hull breach during the suppression event. The chemical contamination scenario: the introduction of a chemical agent from the chemostat zone's H2S into the inhabited atmospheric volume through a failed double gate configuration's inner gate breach, requires the chemical isolation that the gate mechanism provides and the atmospheric monitoring's rapid detection that the chemical contamination event has occurred. The coordinating system's chemical sensors in the deep gallery's inhabited sections provide continuous H2S concentration monitoring at the sensitivity that the immediately dangerous concentration thresholds management requires. Detection above the alert threshold, below the immediately dangerous threshold but above the baseline, triggers the coordinating system's chemical isolation protocol, the inner gate's closure at the affected gallery section's boundaries, the ventilation purge of the affected section's atmosphere through the atmospheric management system's purge mode, and the terraform operator's notification for the outer gate inspection and repair authorization. The biological contamination scenario: the introduction of a biological agent from an aquaculture gallery's disease event into the freshwater zone's water column, which shares the crystal tube's exterior surface with the inhabited atmospheric enclosure, requires the water quality isolation that the gate mechanism provides across the crystal tube sections carrying water from the affected aquaculture gallery and the biological monitoring's rapid detection of the disease event through the aquaculture management layer's continuous biological census data. The contaminated water's isolation from the uninvolved crystal tube section's exterior surfaces limits the biological contamination events spread through the water column to the affected aquaculture gallery section's water volume, while the adjacent uninvolved section's water exchange continues within their own compartment boundaries. 3 hazard classes: hydraulic breach, chemical contamination, biological contamination, each requiring the same gate mechanism's compartment isolation, each triggering the isolation through different detection pathways, each resulting in the same isolated compartment whose atmospheric integrity is preserved for the affected population's self-sufficiency period. The gate is the universal isolation mechanism. The detection pathway is hazard-specific. The isolation response is architecture. The compartment map. The coordinating system's safety management layer maintains a real-time compartment map, a representation of the installation's full 3-dimensional atmospheric volume organized by compartment boundaries, with the current status of every gate in the network displayed at each boundary position. The compartment map is the coordinating system's visual representation of the safety architecture's current state, which compartments are isolated, which are connected, which gates are in the open position and which have been triggered to the closed position by recent formation events. The compartment map is displayed on every Crystal Tube Network's hub-level display, on the Terraform operator's monitoring interface at every Cenote hub, and on the transit pod's navigation display alongside the route management information. The compartment map is not the visitor experience's AR system's content. It is not displayed in the Scaphandar visor's ambient tier or the Safari pod's hull display substrate. The compartment map is the operational safety management's primary situational awareness tool, displayed to the personnel whose decisions depend on knowing the safety architecture's current configuration. The Terraform operator's morning monitoring review includes the compartment map's overnight status, which gates closed during the night in response to formation events, which collar failure events triggered gate closures, which gate closures have been resolved through breach repair and biological monitoring confirmation of recovery, and which remain active with ongoing isolation. The overnight compartment maps review is the Terraform operator's most direct daily engagement with the formation's geological behavior across the sleep period, the formation's events expressed in the safety architecture's gate closure responses, summarized in the compartment map's current status. A compartment map with multiple overnight gate closures in adjacent zones indicates a geological active period in the Chicxulub fracture network stress release, multiple collar failure events in sequence, each triggering the adjacent gate's Venturi responses, each recorded in the digital twin's geological event record. The Terraform operator's assessment of the compartment map's multiple closures is the first step in the geological assessment that the formation event sequence requires. Is the multiple closure event a statistical coincidence of independent failures, or is it a spatial-temporal cluster that the geological model should interpret as a connected stress release event requiring a revision of the formation's current stress state in the affected zone? The assessment is the Terraform operator's professional function, the geological and ecological expertise that the certification program produces, applied to the specific formation data that the overnight's events have generated. The coordinating system's geological model provides the quantitative analysis, the spatial-temporal clustering statistics, the comparison to the historical event record in the digital twin, the geological model's stress field update from the new data. The Terraform operator's judgment is the qualitative assessment, whether the quantitative analysis's conclusion is consistent with the Terraform operator's direct observational knowledge of the formation's recent behavior at this cenote. The Terraform operator's concurrent authorization for resuming visitor activity in the affected zones is the output of this assessment. The authorization confirms that the formation's current stress state, as assessed by the geological model's update and the Terraform operator's professional judgment, is within the visitor management protocol's acceptable range. The authorization is not routine, it requires the active synthesis of quantitative and qualitative information about the formation's current state. The morning monitoring review's compartment map is the starting point for this synthesis. Population management during formation events. The compartment design self-sufficiency period specifies the maximum duration the compartment can sustain its population in isolation. The population management during formation events is the operational protocol that ensures the population's distribution across the compartment map's active isolation zones is within each isolated compartment's self-sufficiency period for that compartment's current population. The population management protocol is the coordinating system's transit management layer's emergency mode, the real-time tracking of every occupied crystal tube section, every docked cycle sub, every Scaphandar participant's position in the freshwater zone, every accommodation section's occupancy status, mapped against the current compartment map's isolation configuration and each isolated compartment's self-sufficiency period at the current population's resource consumption rate. The resource consumption rate tracking is the population management protocol's most dynamic element, the coordinating system's metabolic monitoring layer, the same layer that the residential zone's atmospheric CO2 management uses to track the sleeping occupants' metabolic rates, provides real-time metabolic rate data for all personnel in the isolated compartments. The elevated metabolic rate from the emergency stress response is directly measured, not assumed at the design basis elevated rate that the self-sufficiency period calculation uses as a conservative estimate. The real measured metabolic rate in each isolated compartment at each moment is the actual resource consumption rate, compared against the compartment's remaining resource inventory to produce a real-time remaining self-sufficiency period for each compartment. The remaining self-sufficiency period for the compartment with the most stressed resource inventory, the compartment where the combination of high metabolic rate and high initial population has consumed the largest fraction of the 72-hour design basis resource inventory, is the coordinating system's primary population management alert indicator. When this indicator falls below the threshold that the safe evacuation time from that compartment requires, the coordinating system's population management protocol activates the evacuation routing through whatever crystal tube sections the current compartment map's gate configuration has maintained in connectivity. The evacuation routing is not a fixed plan, it is a real-time calculation from the current compartment map's connectivity status. The breach events that produced the current isolation configuration have eliminated some crystal tube sections' connectivity. The remaining connectivity, the sections whose gates remain open or whose gates the breach events have not triggered, is the evacuation routes option set. The coordinating system's evacuation routing algorithm identifies the shortest time path from each occupied isolated compartment to the nearest self-sufficient zone through the available connectivity. The evacuation routing algorithm's output is the transit management layer's emergency mode routing instructions. Every cycle sub in the transit network receives a destination instruction. Every maintenance sub receives a routing instruction. Every scavenger participant's wrist-mounted direction indicator receives a navigation instruction. Every accommodation section's display panel receives an evacuation direction instruction. The simultaneous routing of all personnel through the available connectivity is the population management protocol's operational expression, not a broadcast evacuation announcement that directs everyone toward the same exit, but individual routing instructions that distribute the evacuation load across the available connectivity to prevent congestion at the bottleneck sections that the compartment map's current configuration has created. The evacuation routing's distribution of the load is the population management protocol's most safety-critical function in a multi-compartment formation event. The compartment that is most resource-stressed and nearest to self-sufficiency period exhaustion is the compartment whose population the routing prioritizes. The compartments with more remaining self-sufficiency period receive their routing instructions in the sequence that the priority ordering allows, not simultaneously with the highest priority compartment's evacuation. The sequential prioritization ensures that the evacuation routing does not create congestion at the bottleneck sections that would delay the highest priority evacuation. The coordinating system's evacuation routing algorithm is the most computationally demanding calculation the classical neural compute layer performs in real-time formation event management, the simultaneous optimization of multiple populations routing through a dynamically changing connectivity graph, with priority ordering constraints and congestion avoidance requirements. The computation completes in the time the transit management layer's routing distribution protocol requires, within seconds of the triggering event, because the algorithm has been operating continuously in the background, maintaining an up-to-date routing solution from the current compartment map's configuration, and only requires updating when the configuration changes rather than computing from scratch in the formation event's response window. The background computation is the real-time safety management's most important design property. The evacuation routing is available the instant it is needed because it has been computing continuously since the last configuration change. The formation event does not trigger the computation. It triggers the distribution of a computation that is already complete. The compartment design's relationship to the living underworld. The compartment design's spatial organization of the cenote installation's atmospheric volumes reflects the safety architecture's hazard analysis, the identification of which zones share which hazard scenarios, which boundary locations produce the most effective DSI isolation, and which self-sufficiency period specifications match each zone's occupancy type's vulnerability characteristics. The spatial organization that the safety architecture produces is not the spatial organization that the operational efficiency criteria would produce in isolation. The most operationally efficient cenote installation would minimize the number of gate transitions that transit, cargo, and personnel must pass through in the daily operational cycle. Fewer gates mean fewer docking sequences, fewer pressure equalization events, fewer mechanical transactions between adjacent zones. The safety architecture requires more gates than operational efficiency prefers, because more gates provide more granular DSI isolation. The tension between operational efficiency and safety architecture granularity is managed in the Crystal Tube Standards gate position specification through the minimum gate spacing requirement, the minimum distance between adjacent gate positions that maintains the DSI isolation's effectiveness while avoiding the operational efficiency penalty of gates so densely positioned that every routine transit involves multiple gate transitions. The minimum spacing is derived from the self-sufficiency period calculation, the minimum segment volume that provides the required self-sufficiency period at the design basis occupancy and metabolic rate is the minimum segment length whose gate positions can be separated without reducing the isolation's self-sufficiency capability below the specification. Above this minimum, the gate positions are placed at the functional boundaries that the compartment concept defines, the residential zone's boundaries, the transit hub's boundaries, the deep gallery's segmentation points, the aquaculture gallery's zone boundaries with the transit corridor. Functional boundaries are the gate positions that produce the most operationally coherent compartments, the compartments that correspond to the inhabited functions that share occupancy types, atmospheric requirements, and evacuation routing through the same crystal tube sections. The compartment map's boundaries are the functional organization of the installation made visible in the safety architecture's isolation provisions. The residential zone, the transit hub, the research zone, the aquaculture production zone, these are not only the operational organization of the cenote installation's functional program. They are the safety architecture's compartment definitions, whose boundaries the gates enforce. The functional organization and the safety architecture are the same organization expressed in two languages, the operational program's language of function and adjacency, and the safety architecture's language of isolation and self-sufficiency. A city whose functional organization is its safety architecture, whose zone boundaries are its safety boundaries, whose gate positions are its evacuation routes, whose self-sufficiency specifications are its neighborhood plans, is a city that does not need to add safety to its design. Safety is the design. The compartmentalized city is the functional city whose program has been organized to reflect the safety architecture's requirements from the first design decision rather than from the last. What the compartmentalized city produces. The compartmentalized city's most significant output is not the safety performance it achieves, the survival of formation events without cascade, the evacuation routing that prevents self-sufficiency period exhaustion, the chemical isolation that contains H2S intrusions to the affected deep gallery segment. These are the safety performance metrics, and they are significant. But the most significant output is the culture of spatial awareness that compartment design produces in the installation's permanent population. A permanent resident who knows the compartment map, who understands which gate boundaries separate their accommodation section from the communal gallery, which gate positions separate the residential zone from the transit hub, and which self-sufficiency period their compartment's resource inventory provides, is a permanent resident who is not surprised by the safety architecture's spatial features. The gate in the communal gallery is not an unfamiliar obstacle. It is the residential zone's boundary marker, visible, understood, incorporated into the resident's spatial understanding of the installation's organization. The resident who understands the compartment map responds to a formation event's gate closure not with spatial disorientation but with situational awareness. The gate that has just closed is the gate at the communal gallery's boundary, which means the breach is in the section beyond that gate, which means the residential zone's resource inventory provides 72 hours of self-sufficiency, which means the Terraform operator's assessment and repair authorization will resolve the isolation before resource exhaustion with the required safety factor. The resident who knows this is not managing an emergency. They are managing a known protocol that the safety architecture was designed to support. The culture of spatial awareness is the compartmentalized city's human safety provision, the architectural and educational preparation of the permanent population to understand and respond correctly to the safety architecture's provisions without requiring real-time instruction from the coordinating system's emergency management layer. The coordinating system provides the routing instructions. The spatial awareness provides the population's capacity to receive and follow those instructions correctly without the confusion that spatial disorientation produces in emergency response. The Founding Charter's Permanent Resident Orientation Program specifies the compartment map study as a residency prerequisite, not a memorization exercise but a spatial comprehension requirement. The resident who cannot navigate the compartment map's boundaries by memory during the orientation program's simulated formation event exercises does not receive the residency authorization that the Terraform operator's concurrent approval requires. The compartment map is the residency entrance examination's primary content. The resident's spatial awareness of the safety architecture is the residency qualification. A civilization that makes safety architecture literacy a precondition for permanent residency has made the safety architecture's culture the residency culture. The permanent residents are the population that understands the safety architecture. The safety architecture produces the culture of spatial awareness. The culture of spatial awareness produces the safety response effectiveness. The effectiveness is the safety architecture's purpose. The culture is the purpose's human expression. The compartmentalized city is safe because it is understood. The understanding is the safety. Cross-references, Part 2, CH4, The Crystal Tube Standard, Part 3, CH5, Skyscrapers Beneath the Canopy, Part 6, CH5, Sleeping Inside the Aquifer, Part 7, CH1, Breakaway Architecture, Part 7, CH2, Automatic Bulkheads, Part 7, CH4, Living Through Failure, Part 7, CH5, The Blackout Protocol, Part 9, CH4, Redeemer's Governance OS. For compartment self-sufficiency period calculation methodology and resource inventory specification by compartment type, see Appendix D, Construction Operations Manual. For fire suppression agent specification and chemical contamination isolation protocol, see Appendix D, Construction Operations Manual. For compartment map display protocol and Terraform operator morning review format for gate status assessment, see Appendix H, Governance Operations Manual. For evacuation routing algorithm specification and background computation protocol, see Appendix D, Construction Operations Manual. For permanent resident orientation program compartment map literacy requirements and residency authorization criteria, see Appendix H, Governance Operations Manual. Living through failure. The surface world safety culture has a foundational epistemological problem. It treats failure as evidence of the safety system's inadequacy rather than as evidence of the environment's actual behavior. When the bridge collapses, the safety system failed. When the dam breaches, the safety system failed. When the building burns, the safety system failed. The failure is defined as the safety system's failure regardless of whether the safety system performed exactly as designed, regardless of whether the collar shattered cleanly, the gate sealed correctly, and the compartment maintained its atmospheric integrity, because the surface world safety standard is not failure managed correctly but failure prevented entirely. This epistemological position produces a specific pathology in surface world safety culture. The failure that the safety system managed correctly is reported as the safety system's failure rather than as the formation's behavior and the safety system's designed response. The formation event that the collar absorbed kinetically, that the gate sealed hydraulically, and that the compartment contained within its self-sufficiency period is reported, in the incident report, in the regulatory review, in the press coverage, as the collapse, the breach, the emergency. The managed failure is the reported failure. The safety system's designed performance is the incident. This pathology has the consequence that every managed failure produces a demand for the safety system's revision to prevent the failure rather than to manage it better. The revision is typically a stricter specification that reduces the managed failure's frequency at the cost of increasing the unmanaged failure's severity when the formation event exceeds the stricter specification's threshold. The surface world safety culture responds to managed failures by demanding systems that manage fewer failures, systems that prevent more events from reaching the managed failure threshold. The events that exceed the prevention threshold, when they occur, are unmanaged because the management infrastructure was not designed for them. The events that exceed the stricter prevention threshold are larger, more severe, and less frequent than the events the previous threshold managed. When they occur, they are catastrophic rather than managed. Pipe dream safety culture inverts this. Failure is the formation's communication, correctly received when the safety system's designed response manages it within the designed parameters. Living through failure is the safety system's purpose, not its limitation. The civilization that lives through formation events has a safety system that is working. The civilization that prevents all formation events has a safety system that is claiming to control the formation, a claim that the geological timescale will eventually falsify in the most consequential way possible. What living through failure requires? Living through failure is not passive. It is not the acceptance of whatever the formation produces and the hope that the safety system's managed response is sufficient. Living through failure is an active safety posture, a continuous practice of maintaining the readiness to manage failure correctly when it occurs, improving the failure management's quality with each managed failure event, and using the managed failure's geological data to improve the formation model that the next managed failure's response will be based on. Living through failure requires 5 simultaneous competencies that the founding charter's safety culture specifies as the installation's permanent operational requirements. The first is response readiness, the maintenance of every safety provision at its designed performance specification at all times, not only during the event probability elevated periods when the geological monitoring has identified elevated formation stress. The collar's material specification is maintained across the full maintenance cycle. The gate's latch spring is replaced before the condition monitoring's threshold. The compartment's resource inventory is replenished before the self-sufficiency period calculation identifies a shortage. The supercapacitor bank's charge state is maintained by the streaming potential harvest's continuous operation. Response readiness is not emergency preparedness, it is the permanent operational state of a safety system that must be available at any moment the formation produces an event. The second is formation literacy, the population's understanding of what the formation is doing and what the safety system's response means. The permanent resident who does not understand the collar failure's geological significance, who experiences the collar failure's acoustic event as an unexplained noise rather than as the formation's communication, cannot contribute to the living through failure culture's active posture. Formation literacy is the population's capacity to read the formation's behavior through the safety system's designed responses, to understand what the compartment isolation means geologically, and to respond to the safety system's designed responses with the behavioral competence that the evacuation routing and the resource management protocols require. The third is response quality improvement, the systematic incorporation of each managed failure event's data into the safety system specifications, the formation model's calibration, and the response protocol's refinement. Each collar failure updates the replacement collar specification. Each gate closure event updates the gate's latch spring replacement schedule based on the Venturi trigger's activation characteristics in the specific formation conditions the event occurred in. Each compartment isolation event updates the self-sufficiency period calculation's metabolic rate assumption based on the actual metabolic rates the coordinating system's monitoring measured in the isolated population during the event. The managed failure is the training event. The training event improves the next managed failure's management quality. The fourth is the distinction between managed and unmanaged failure, the safety culture's capacity to recognize when a failure event's management has succeeded and when it has not, and to assess the difference without the surface world's epistemological pathology that treats any failure as the safety system's failure. The managed failure that stayed within the designed collar's failure threshold, that produced the Venturi trigger's clean closure, that maintained the compartment's atmospheric integrity throughout the self-sufficiency period, this is the safety system's success, not its failure. The unmanaged failure that exceeded the collar's design threshold, that produced a cascade the gate could not prevent because the cascade velocity exceeded the Venturi trigger's response window, that resulted in a compartment's resource exhaustion before the evacuation routing could complete, this is the safety system's failure, and the distinction matters because the responses to success and failure are different in kind. The fifth is the governance protection of the safety culture, the institutional mechanisms that prevent the surface world's epistemological pathology from replacing the managed failure's correct assessment, success, with the surface world's pathological assessment, failure. The REDEEM framework safety incident reporting standard specifies the assessment criteria. A formation event is reported as managed when the safety system's designed response was activated and the event was contained within the designed parameters. A formation event is reported as unmanaged when the designed response was activated but the event exceeded the designed parameters. A formation event is reported as a safety system failure when the designed response was not activated and should have been, or when the designed response was activated incorrectly. The three categories are constitutionally distinct. The distinction's protection from reclassification is the REDEEM framework's most important safety governance function. The psychological architecture of managed failure. The occupant of a crystal tube section who experiences a collar failure event, who hears the acoustic signature of the frangible ceramic composite's clean fracture through the tube wall's vibration conduction, who sees the coordinating system's amber alert indicator appear on the ambient tears display, who experiences the transit pod's supercapacitor magnetic braking deceleration from boulevard speed to rest, is experiencing the formation event's managed response. This is a psychologically intense experience. The acoustic event is loud. The deceleration is firm. The alert indicator communicates that a safety event has occurred. The experience's sensory intensity is real and is not the formation event's management's failure. The psychological architecture of living through failure requires that the managed failure's sensory intensity does not produce the psychological response that the surface world safety culture produces, the demand for a system that prevents the sensory intensity from occurring. The formation event's sensory intensity is the collar failure's acoustic signature and the gate's closure's deceleration, the designed responses to the formation's geological event. The designed responses are not more intense than necessary. They are as intense as the geological event and the safety physics require. Preventing the sensory intensity requires preventing the designed response, which requires preventing the geological event. Preventing geological events is not within the safety architecture's capability. The sensory intensity is the formation event's managed consequence. The psychological architecture that supports living through managed failure is prepared expectation, the experiential state of occupants who have been trained in what the formation event's managed response looks, sounds, and feels like, so that the sensory intensity during the event is recognized as the expected managed response rather than experienced as the unexpected failure. Prepared expectation converts the acute stress response to managed alarm, a state of heightened attention and appropriate behavioral response rather than the unmanaged panic that the unexpected produces. The residential zone's permanent residents achieve prepared expectation through the orientation program's simulated formation event exercises, acoustic recordings of collar failure events at the ambient loudness the tube wall's vibration conduction produces in the residential zone, played during the orientation's formation event simulation while the resident practices the compartment map's evacuation routing. The simulation's sensory content is calibrated to the actual formation event's sensory experience at the residential zone's typical distance from collar failure events, close enough to be realistic, far enough from the simulated event's epicenter to represent the typical rather than the worst-case sensory experience. The longevity program's enrolled participants receive a formation event orientation session during the first week's enrollment period, before the longitudinal protocol's depth assignment has placed them in the residential zone's therapeutic pressure range, that describes the formation event's expected sensory characteristics, demonstrates the compartment isolation protocol's visible elements, the gate's closure visible through the communal gallery's transparent walls as the acoustic event occurs, and walks the participant through the behavioral response the evacuation protocol requires. The orientation session does not simulate the full acoustic intensity of the formation event. It prepares the participant to recognize what the actual event will be when it occurs. The adventure program's participants receive the formation event orientation as the final component of the scavenger training session that precedes every dive, what the collar failure's acoustic signature sounds like transmitted through the alone visor's helmet, what the gate closure looks like in the crystal tube visible through the visor's optical field, and what the behavioral response, terminate the dive's current position, activate the Avalo system's neutral buoyancy trim, navigate toward the nearest wetlock using the strontium illuminate markers guidance, requires in the open freshwater zone outside the crystal tube network's protected volumes. The behavioral response for the scavenger participant in the open freshwater zone during a formation event is the safety architecture's most individual provision. The participant is outside the crystal tube network's gate protection during a dive, in the freshwater zone's open water column, which is not a pressurized atmospheric enclosure and therefore not subject to the breach event's atmospheric integrity loss that the gate mechanism isolates. The formation event's primary impact on the scavenger participant in the open freshwater zone is the acoustic and hydraulic disturbance that the collar failure's fracture produces, intense at close range, manageable at the typical dive zone's distance from the collar positions. The behavioral response is to navigate toward the nearest wetlock at the dive zone's available crystal tube section, dock, and enter the crystal tube network's protected atmospheric environment before the hydraulic disturbance's water turbidity reduces visibility to below the strontium illuminate marker's effective navigation range. The formation event's response is different for every occupancy type and every position within the installation. The collar failure's managed response is the same safety architecture's designed response. The behavioral requirement is position-specific. The prepared expectation is occupancy type specific. The safety culture that supports living through failure is the integration of these specific preparations into a population-wide readiness that the formation can test without catastrophic consequence because the preparation is complete. The incident record. The digital twin safety incident record is the living through failure culture's institutional memory, the documented history of every managed failure event across the installation's operating period, with the formation data, the safety system response metrics, the population behavior assessment, and the outcome indicators that together constitute the evidence base for the safety culture's continuous improvement. The incident record is not an incident register in the surface world sense, not a list of events that the safety systems management categorizes as incidents because the surface world's epistemological position treats all formation events as incidents regardless of the management quality. The digital twin's incident record categorizes events by the three categories the Redeemer Framework Safety Incident Reporting Standard specifies: managed events, unmanaged events, and safety system failures. The categorization is the record's most important content, the classification of whether the safety system performed as designed, exceeded its designed capacity, or failed to perform. The managed event record is the formation's geological autobiography through the safety system's response, the collar failure events and their spatial temporal distribution that the geological model stress analysis incorporates, the gate closure events and the Venturi triggers activation characteristics that the gate maintenance protocol's condition monitoring uses, the compartment isolation events and the resource consumption rates and behavioral response data that the self-sufficiency period calculation and the evacuation routing algorithm incorporate. Each managed events record is a training data point that the safety system's continuous improvement process uses. The unmanaged event record is the safety architecture's most important improvement input, the events where the designed safety response was activated but the event exceeded the designed parameters. These are the events where the collar failed but the fracture produced fragments larger than the specification settling time criterion, where the formation event's energy exceeded what the specified failure threshold absorbed, producing fracture energy transmission to the adjacent section. These are the events where the gate closed correctly but the seal's compliance allowed leakage above the specification's tolerance, where the formation event's pressure differential exceeded what the seal's compression capacity produced. These are the events where the compartment maintained atmospheric integrity but the resource consumption rate exceeded the self-sufficiency period calculation's conservative metabolic rate assumption, where the actual stress response's elevated metabolic rate in the actual population exceeded the design basis. The unmanaged event record drives specification revisions, the collar specification's failure threshold updated to absorb the unmanaged event's energy, the seal's compliance specification revised to maintain the leakage tolerance at the unmanaged event's pressure differential, the self-sufficiency period calculation's metabolic rate assumption revised upward to match the actual stress response data. The specification revisions are the safety architecture's response to the unmanaged event, not the demand for prevention but the improvement of management. The safety system failure record is the rarest category and the most consequential, the events where the designed response was not activated when it should have been, or was activated incorrectly. These events require the full investigation protocol that the Redeemer Framework Safety Governance specifies, the coordinating system's event reconstruction from the sensor data, the digital twins timeline analysis, the Terraform operator's concurrent investigation authorization, the Safety Technical Working Group's root cause analysis, and the Network Governance Council's specification revision authorization. The Safety System Failure Records Investigation Protocol is structured to identify whether the failure was a component failure, a specific safety provision that did not perform within its specification, or a specification failure, a safety provision that performed within its specification but whose specification was insufficient for the formation event it encountered. Component failures drive maintenance protocol revisions and component design improvements. Specification failures drive the Founding Charter Safety Standard Revision process, the constitutional process that the Redeemer Framework specifies for changes to the safety architecture's fundamental parameters. The distinction between component failure and specification failure is the safety culture's most demanding analytical requirement. It requires the Safety Technical Working Group to assess not just what happened but what the designed response should have been. A collar that failed in the wrong mode failed as a component, its material was not within specification. A collar that failed in the designed mode at an energy level below the specification's threshold failed as a specification, the specification's threshold was too high for the formation event's energy. The analysis requires the digital twins event reconstruction at the spatial and temporal resolution that distinguishes between the two failure types. The event reconstruction's quality is the analysis's limiting constraint. The digital twins event reconstruction capability improves with the installation's operating history, the formation model's calibration accuracy at each collar position, the acoustic monitoring signal quality at each transceiver node's position relative to the event's source, and the geological model's stress field reconstruction accuracy at the event's location are all higher after 10 years of operational data than after the founding year's first formation events. The safety system failure investigation's analysis quality improves with the digital twins improving event reconstruction capability. The later safety system failure investigations are more precise than the earlier ones. The precision improvement is the managed failure culture's compound return on the incident record's maintenance. The Terraform operator's role in living through failure. The Terraform operator's concurrent authority in the safety architecture's formation event response has been documented across the preceding chapters: the caller failure's Terraform operator notification, the gate closure's Terraform operator assessment and restoration authorization, the compartment isolation's evacuation routing authorization, the chemical contamination's repair authorization. Each concurrent authority requirement is a specification of the human judgment layer's function in the safety response sequence. The Terraform operator's function in living through failure is not the emergency management function that the surface world's safety culture assigns to the first responder, the person who arrives at the failure event and manages its immediate consequences. The coordinating system manages the immediate consequences, the automated restrictions, the evacuation routing, the atmospheric management adjustments. The Terraform operator's function is the assessment function, the professional judgment that the coordinating system's quantitative analysis cannot replace because it requires the integration of the formation's current behavior with the knowledge of the formation's historical behavior that the Terraform operator's direct operational experience provides. The assessment function has three components that the Terraform operator certification program specifically develops. The first is the geological assessment, the judgment of whether the formation event's safety system response indicators, the caller failure's location and energy, the gate closure's Venturi trigger activation characteristics, the geological model's stress field update, are consistent with the formation's historical behavior at this location or indicate a new geological condition that the historical model does not capture. The second is the biological assessment, the judgment of whether the formation event's biological impact indicators, the Bodo population's behavioral recovery timeline, the synthetic reef's post-event succession trajectory, the cave fish community's spatial distribution in the affected zone, are within the expected recovery parameters or indicate an ecological condition that the Biological Management Protocol's standard recovery framework does not address. The third is the operational assessment, the judgment of whether the formation event's management outcome, the compartment's self-sufficiency period was not exceeded, the evacuation routing completed without resource exhaustion, the safety system's response metrics are within the designed parameters, confirms the managed event category or indicates an unmanaged event or safety system failure that the incident records investigation protocol must address. All three assessments are documented in the Terraform operator's post-event assessment report, which is the legal record of the managed failure event's outcome assessment. The assessment report is the REDEEM framework's formation event closure document, the document whose filing in the digital twin safety incident record closes the event's active management phase and opens the continuous improvement phase whose inputs the three assessments provide. The assessment report's filing requires the Terraform operator's authorized digital signature, the biometric authentication that the REDEEM framework's identity management system requires for all legally significant actions in the governance record. The signature confirms that the Terraform operator has performed the three assessments, that the assessments are consistent with the coordinating system's quantitative analysis of the event data, and that the event categorization the report applies, managed, unmanaged, or safety system failure, reflects the Terraform operator's professional judgment rather than the coordinating system's algorithmic classification. The distinction between the Terraform operator's professional judgment and the coordinating system's algorithmic classification is constitutionally maintained by the assessment report's requirement for the human signature. The coordinating system's classification of the event is the assessment report's input, not its output. The output is the Terraform operator's professionally responsible classification, which may or may not concur with the coordinating system's algorithmic classification. When the two concur, the assessment is straightforward. When they diverge, the divergence is the signal that the event's geological or biological character has produced an outcome that the coordinating system's quantitative models did not predict, which is the most important divergence the incident record can document, because it is the signal that the models require revision. The Terraform operator's divergence from the coordinating system's classification is not a criticism of the coordinating system's analytical quality. It is the formation's geological or biological expression of something the coordinating system's current models do not capture, and the Terraform operator, whose professional expertise is the direct observation of what the formation does and what the safety system produces in response, is the human sensor that can detect the model's gap and document it in the assessment report's divergence record. The divergence record is the digital twin's most valuable safety data input, the evidence that the coordinating system's current models have encountered a formation condition they do not fully describe. The divergence record drives the model revision that the assessment's second iteration will confirm or correct. The Terraform operator's professional judgment is the model's most precise correction instrument. The failure that did not happen. Every formation event that the safety architecture manages correctly is a failure that the safety architecture prevented in the specific sense that matters. The catastrophic cascade was prevented. The collar failed. The gate sealed. The compartment isolated. The population managed. The cascade did not occur. The failure was the formation event. The prevention was the safety system's managed response. The failure that did not happen is the cascade. The cascade failure that the safety architecture prevented leaves no record in the incident report because it did not occur. The collar failure is in the managed event record. The gate closure is in the managed event record. The compartment isolation is in the managed event record. The cascade that did not propagate is not in any record because it did not happen. It cannot be observed that it would have happened without the safety system's response, except through the counterfactual analysis that the digital twins event reconstruction and the formation model's stress propagation simulation can produce. The safety architecture's greatest successes are invisible: the cascade that the collar's clean fracture decoupled kinetically before the gate's Venturi trigger received the hydraulic signal, so that by the time the gate closed the inrush was already isolated within the affected section and the adjacent section's atmospheric integrity was never at risk. The formation event occurred. The safety system responded. The cascade that would have propagated without the response did not propagate. There is no cascade in the incident record. There is only the collar failure and the gate closure, the managed events components, present in the record as managed events. The living through failure culture acknowledges the invisible success explicitly. The managed events record is read not only as the documentation of what happened, the collar failed, the gate closed, but as the evidence of what did not happen, the cascade was not produced. Reading the managed event record as only what happened, without acknowledging what did not happen, is reading the safety architecture success as a near miss. A near miss framing produces the surface world's pathological response, the demand for a system that prevents the collar from failing, the gate from closing, the managed event from occurring. The Founding Charter's Safety Incident Reporting Standard explicitly addresses this. Managed events are reported as the formation event's designed response activation, not as near miss events. The language in the incident report: collar failure at position X, designed fracture mode confirmed, gate closure at adjacent position Y, Venturi activation confirmed, compartment Z isolated, population managed within self-sufficiency period, is the language of a safety system performing correctly, not the language of a safety system having a close call. The language shapes the culture. The culture produces the epistemological position. The epistemological position determines whether the next managed failure event drives the demand for prevention or the drive for better management. The drive for better management is the living through failure culture's continuous improvement engine. Each managed events record provides the data that makes the next managed events management better. The collar specification improves. The gate seal compliance is refined. The compartment's resource inventory is calibrated to the actual metabolic rate data. The evacuation routing algorithm's background computation is updated with the actual connectivity graph's current configuration. The improvement compounds across the design life. At year 500, the safety architecture manages formation events that at year 1 would have produced unmanaged events or safety system failures, because the 500 years of managed event data have improved the specifications, the models, and the protocols to the precision that 500 years of formation events can calibrate. The formation taught the safety architecture for 500 years. The safety architecture is 500 years better than it was at founding. This improvement is not available to a safety architecture that demands prevention. A safety system that has prevented all formation events has no formation event data to improve its specifications with. The safety system that prevents all formation events maintains the founding year's specifications across the full design life, because the formation has never been allowed to test and improve them. At year 500, the preventive safety system is no better than at year 1. The formation event that finally exceeds the preventive threshold produces the same safety system that was designed at founding, the founding year's specification against a 500-year formation event. The living through failure safety system at year 500 is 500 years of managed events more precise than at year 1. The preventive safety system at year 500 is unchanged from year 1. When the formation produces an event that exceeds both systems' founding year specifications, one system has 500 years of improvement to draw on. The other has the founding year's design. Living through failure is the investment. The compound return is safety. The human factors. The safety culture's human factors are the provisions for the human beings inside the safety architecture during the formation events the architecture manages, not the operational provisions for managing the event, which the preceding sections address, but the experiential provisions for the people whose bodies and psychological states are inside the formation events managed response. The formation events managed response is frightening. The collar failure's acoustic event is alarming. The gate closure's magnetic braking deceleration is disorienting. The compartment isolation's atmospheric enclosure without the crystal tube network's normal transit connectivity is confining. The resource consumption monitoring's display of the remaining self-sufficiency period is anxiety-producing. These are real human experiences. They are the formation events managed responses' experiential consequences for the people inside the management. The human factors provisions address these experiences not by eliminating them: the acoustic event's intensity, the deceleration's firmness, the compartment's confinement, the monitoring display's remaining self-sufficiency period are all correctly calibrated to the formation event's managed response parameters and cannot be reduced without reducing the safety system's response quality, but by preparing the experience's recipients to manage the experiences correctly. The prepared expectation that the formation event orientation produces is the primary human factors provision. The resident or participant who has heard a realistic acoustic reproduction of the collar failure's sound, who has experienced a deceleration profile in the transit simulation that approximates the magnetic braking's characteristics, who has practiced the compartment maps evacuation routing in a simulated isolation condition. This person has a psychological model for what the formation event's managed response feels like before the first event occurs. The model is not exact. The simulation cannot fully replicate the real event's sensory intensity. But the model reduces the gap between what the person expected and what the event produces, reduces the psychological mismatch that produces panic. The post-event psychological support is the human factors provision that the founding charter specifies as a standard operational requirement rather than an exceptional response to an exceptional event. After every compartment isolation event, regardless of duration, the Terraform operator's daily monitoring includes the psychosocial indicators for the isolated compartment's occupants. Not because the isolation event is expected to produce trauma in a well-prepared population, prepared expectation and successful management reduce the psychological impact to the stress response range, but because the monitoring's presence communicates to the affected occupants that their psychological experience of the formation event is recognized as part of the event's management, not only their physical safety. The recognition is the safety culture's most human provision. The formation event's management includes the people inside it, not only the atmospheric integrity and the resource consumption metrics that the coordinating system monitors. The Terraform operator's acknowledgement of the affected population's psychological experience is the human judgment layer's most personal contribution to the living through failure culture, the recognition that living through failure is something people do, not something the safety system achieves on the people's behalf. The people live through the failure. The safety system makes the living possible. The culture makes the living meaningful, contextualizes the formation event's managed response within the civilization's relationship to the formation, which is a relationship that includes the formation's geological behavior as a fact to be lived with rather than prevented. The culture's contextualization is the final human factor, the understanding that the formation event that the safety system managed is evidence that the civilization is inside a geological system that produces geological events, and that the civilization's presence inside this system is a relationship, and that the relationship includes the respect for the formation's geological behavior that the safety architecture's design embodies. The formation produced an event. The safety architecture managed it. The civilization continues inside the formation. The relationship continues. This is what living through failure means. The failure that must not happen. The living through failure culture's commitment to managed failure improvement has a boundary. The failure that the safety architecture must not produce is the failure that the managed failure culture cannot recover from. The cascade that the breakaway architecture prevents, the atmospheric loss that the automatic bulkheads seal, the resource exhaustion that the compartment design avoids, these are the failures that the safety architecture's designed response prevents. They are the failures on the other side of the managed failure's boundary. The safety architecture's design envelope specifies the boundary. The formation events within the design envelope produce managed failures. The formation events outside the design envelope produce the failures that the safety architecture cannot manage with the designed provisions. The design envelope specification is the safety architecture's honest acknowledgement that its managed failure culture's commitment extends to the formation events the geological model's worst-case historical analysis documents, and not to the formation events whose probability the geological model cannot bound within the historical record. The formation events outside the design envelope are not the safety architecture's failure. They are the formation's expression of geological behavior that the historical record, the Speleothem Paleoclimate record's 10,000 years of event documentation, has not previously produced. These events are possible. Geological systems are capable of events outside their historical records. The safety architecture does not claim to manage them. The safety architecture claims to manage the historical record's documented range. The formation events outside the design envelope are managed by the evacuation, the full evacuation of the installation's population to the surface world's atmosphere when the geological monitoring's precursor signals indicate an event is developing that the geological model classifies as potentially outside the design envelope. The evacuation is not a safety architecture provision in the same sense as the collar and the gate. It is the acknowledgement that living through some failure requires leaving the failure's environment before the failure occurs. The evacuation protocol is not a failure of the living through failure culture. It is the culture's expression of the distinction between the failures the safety architecture manages and the failures it does not claim to manage. Evacuating before an out-of-design envelope event is the honest response to the formation's geological expression of something the design envelope did not include. It is the formation's veto right over the civilization's presence, the formation's ability to produce an event that the civilization's safety architecture cannot manage, requiring the civilization to yield the space temporarily. The civilization yields temporarily. The formation produces the event. The geological model assesses the event. The Safety Technical Working Group evaluates whether the design envelope should be revised to include the event's magnitude. If the revision is warranted, the design envelope expands. If the event is assessed as genuinely outside what the installation's safety architecture can manage, the affected cenote installation is permanently evacuated and the network's governance transitions the installation's functions to adjacent cenotes whose design envelopes include the relevant geological event magnitudes. Permanent evacuation is the ultimate managed failure. The formation's geological behavior has exceeded what the civilization can safely inhabit at that location. The civilization acknowledges the limit, evacuates, and continues elsewhere. The habitation record at the evacuated cenote closes. The digital twins formation model retains the installation's geological data as the most precise characterization of the formation's behavior at that location in the full geological record. The data improves the design envelope specifications for the adjacent cenotes. The learning from the evacuation is the managed failure culture's most consequential return, the specific formation location's geological behavior that the design envelope revision incorporates for all subsequent installations. The civilization learns from the places it cannot safely inhabit as well as from the places it can. Both are the formation's teaching. Both are the living through failure culture's curriculum. The failure that must not happen, the cascade, the atmospheric loss, the population harm, is prevented by the safety architecture's managed failure provisions within the design envelope. The failure that must be acknowledged, the design envelope's limit, is managed by the evacuation's honest response to the formation's geological authority. The formation is always right. The safety architecture's job is to be honest about what the formation is saying. What Part 7 has built. For chapters into Part VII's safety architecture, the full safety system is visible as an integrated whole rather than as a collection of individual provisions. Chapter 1's Breakaway architecture is the safety system's geological intelligence layer, the color failure events that train the geological model, the pre-failure stress accumulation that the acoustic monitoring detects, and the clean fracture that decouples the formation event's kinetic energy from the adjacent sections. Chapter 2's automatic bulkheads are the safety system's hydraulic response layer, the Venturi-triggered gate closure that seals the breach event's inrush without sensor latency, the supercapacitor magnetic braking that decelerates the transit pod within human tolerance, and the passive physics that make the response independent of the power supply the formation event might eliminate. Chapter 3's compartmentalized cities are the safety system's spatial organization layer, the compartment boundaries whose self-sufficiency periods provide the population management time the formation event's assessment and repair requires, the evacuation routing whose background computation is always current, and the safety culture's spatial literacy that the permanent population must maintain. Chapter 4's living through failure is the safety system's cultural and epistemological layer, the managed failure's correct categorization, the incident record's improvement input, the terraform operator's professional judgment, and the living through failure culture's distinction between the failures the safety architecture manages and the failures it honestly acknowledges as outside its management. The four layers are integrated. The geological intelligence layer's formation event data improves the hydraulic response layer's specifications. The hydraulic response layer's isolation creates the spatial organization layer's compartment isolation that the living through failure culture's population must navigate. The living through failure culture's incident record drives the geological intelligence layer's model revision. The integration is the safety architecture's emergent property, the whole that is more than the sum of its provisions. The safety architecture is not the safety against failure. It is the architecture for living through failure correctly. The formation produces events. The safety architecture manages them. The civilization lives. Cross-references, Part 1, CH4, Floating Before Anchoring, Part 2, CH6, Designing for 1,000 Years, Part 7, CH1, Breakaway Architecture, Part 7, CH2, Automatic Bulkheads, Part 7, CH3, Compartmentalized Cities, Part 7, CH5, The Blackout Protocol, Part 9, CH4, Redeemer's Governance OS, Part 12, CH5, Sans a priori. For managed failure categorization criteria and incident report format specification, see Appendix H, Governance Operations Manual. For Terraform Operator Post-Event Assessment Protocol and Digital Signature Authentication Requirement, see Appendix H, Governance Operations Manual. For Design Envelope Specification and Evacuation Protocol Trigger Conditions, see Appendix A, Formation Baseline Protocol. For Psychosocial Monitoring Indicators and Post-Event Support Protocol, see Appendix H, Governance Operations Manual. For Safety System Failure Investigation Protocol and Root Cause Analysis Methodology, see Appendix H, Governance Operations Manual. Pipe Dream. Part 7, Safety First. Chapter 5, The Blackout Protocol. Power failures in the surface world are administrative inconveniences whose physical consequences are managed by the backup systems whose existence the regulatory framework requires. The hospital's generator starts. The data center's UPS maintains continuity until the diesel kicks in. The elevator descends to the nearest floor and opens its doors. The traffic lights go dark and drivers revert to the four-way stop convention they barely remember from driver's education. The inconvenience is real. The physical consequences of the surface world's power failure are primarily the cessation of electrically powered services, the lights, the HVAC, the devices, the communications, rather than a threat to the physical integrity of the space the power was supporting. Pipe Dream's power failure is not an administrative inconvenience. The crystal tube network's electromagnetic propulsion system, the atmospheric management system's supply pumps and scrubbers, the light relays diode arrays, the coordinating system's classical and quantum compute layers, the biological management protocol's acoustic transponder network, the structural health monitoring's piezoelectric sensor data stream, and the safety system's supercapacitor braking protocol's discharge control signal, all of these are electrically powered systems whose cessation produces consequences in the freshwater zone's inhabited volume that are not analogous to the surface world's lights going out. The power failure in an inhabited crystal tube section at 30 meters depth with a transit pod in the maglev track produces, the pod's electromagnetic levitation ceases and the pod settles onto the guide rail's physical surface, the maglev propulsion ceases and the pod decelerates to rest on the guide rail without the controlled deceleration the electromagnetic system provides, the pod's interior illumination ceases and the atmospheric management system's fans cease circulation, the coordinating system's transit management layer's navigation data for the pod's display ceases, and the light relay's illumination ceases, leaving the passage in the absolute darkness that has characterized its geological history since before the cenote was formed. The passenger in the pod in this darkness, at 30 meters depth, with the atmospheric management system's passive soda lime scrubbing canister as the only CO2 management, with the guide rail's strontium illuminate markers as the only navigation reference, with the Avalo system's manual valve as the only buoyancy management, and with the flywheel's flywheel storage to mechanical drive coupling as the only propulsion, this passenger is in the blackout protocol's operating condition. The blackout protocol is the safety architecture's provision for this condition, the comprehensive system of passive, non-electrical safety provisions whose combined function is to sustain the passenger's life and deliver them to the nearest wetlock docking port under any complete power failure scenario, without any communication from the coordinating system, without any electrical power from the crystal tube network, and without any external intervention from the installation's maintenance operations that the power failure has also interrupted. The protocol scope. The blackout protocol covers the full power failure scenario, not the partial power failure that takes some electrical systems offline while the streaming potential harvests independent generation maintains others, and not the system failure that disables the coordinating system while the electrical infrastructure remains operational. The full power failure is the scenario where every electrically powered system in the crystal tube network is simultaneously offline, no electromagnetic propulsion, no atmospheric management fans, no light relay illumination, no coordinating system communication, no sensor network data, no safety system control signal. This scenario is the blackout protocol's design basis because it is the worst-case scenario for the electrical infrastructure's simultaneous loss, the scenario that the protocol's provisions must sustain the passenger through without any supplementation from systems the power failure has taken offline. Any provision that the full power failure eliminates is a provision that the blackout protocol cannot rely on. Any provision that the full power failure does not eliminate is a provision the blackout protocol can rely on. The provisions the full power failure eliminates: every system that draws power from the crystal tube network's electrical infrastructure, every system that communicates through the coordinating system's data network, every system that requires the atmospheric management system's active components. The provisions the full power failure does not eliminate: the strontium illuminate rail markers, whose passive phosphorescent glow requires no power source and no activation signal, the soda lime scrubbing canisters, whose chemical CO2 absorption requires no power source and no activation mechanism, the Avalo system's compressed gas reservoir, whose pressure-driven buoyancy control requires no power source and no activation signal, the flywheel's rotational inertia, which stores kinetic energy from the pedaling input without any electrical component, and the supercapacitor bank stored energy, which was charged by the streaming potential harvest before the power failure and whose discharge drives the magnetic braking protocol's coil activation through the gates closure event's independent circuit. The blackout protocol's provisions are all of the second category, passive, physics-based, energy stored, requiring no electrical power and no coordinating system communication to function. The protocol is the safety architecture's most complete expression of the design principle that safety responses must not depend on the infrastructure the hazard attacks. The passenger's immediate experience. The power failure's onset is instantaneous. The crystal tube network's electrical infrastructure does not fail gradually in the full blackout protocol's design basis scenario. The transition from full electromagnetic operation to complete electrical silence happens in the time the electrical fault propagates through the network, milliseconds. The passenger experiences the instantaneous transition. The pod's interior illumination extinguishes, the coordinating system's navigation display goes dark, the electromagnetic propulsion's smooth silent operation transitions to the mechanical contact of the pod settling onto the guide rail's physical surface, and the passage outside the pod's hull transitions from the light relay's illuminated aquifer view to absolute darkness. The absolute darkness deserves specific attention because it is qualitatively different from the darkness that the surface world's power failure produces and that the training protocol cannot fully replicate. The surface world's power failure produces darkness interrupted by the ambient light from windows, the glow of emergency exit signs, the backlit screens of devices on battery power, and the gradual dark adaptation that the human visual system's rod photoreceptors produce across the first 20 minutes of low-light exposure. The surface world's power failure darkness is not absolute because the surface world has ambient light sources that the power failure does not eliminate. The crystal tube network's passage in the full power failure condition has no ambient light source. The cenote's geological darkness, the darkness that preceded the installation's light relay by 66 million years, is the absolute darkness that the human visual system's rod photoreceptors cannot overcome regardless of adaptation time. The absolute darkness is not the darkness where shapes are indistinct. It is the darkness where the visual cortex receives no photon signal from any source. The human visual system in absolute darkness does not process a dark scene. It processes nothing. The visual field is not dark. It is absent. The passenger's first experience of the blackout protocol's absolute darkness is the sensory condition that the training protocol's blackout simulation prepares them for. The training protocol uses complete room darkening at the same level of absolute darkness that the cenote's geological darkness produces, so that the trained passenger has experienced the absence of the visual field before the actual blackout protocol's first occurrence. The prepared expectation converts the absolute darkness from a crisis-inducing sensory deprivation to a recognized operating condition, the condition in which the strontium illuminate markers are the navigation reference and the flywheel is the propulsion and the soda-lime canister is the CO2 management. The trained passenger in absolute darkness orients through the non-visual senses that remain functional, the pod's mechanical contact with the guide rail's physical surface, which the settling sensation communicated, the guide rail's physical surface below the pod, which the mechanical drive's engagement will push against, and the strontium illuminate marker's glow, which appears as the passenger's dark-adapted rod photoreceptors begin to process the marker's emission at the adaptation threshold. The training protocol has established the expected location for the strontium illuminate marker's emission wavelength is in the green spectrum, approximately 520 nanometers, which the human scotopic visual system's rod photoreceptors are most sensitive to under dark-adapted conditions. The marker's emission intensity is calibrated to the minimum required for reliable human detection at the dark-adapted rod photoreceptor's sensitivity threshold, at the maximum distance from the markers at which the passenger in the pod must detect the marker to maintain navigation confidence. The calibration is not the emission intensity that makes the markers most comfortable to see under dark-adapted conditions. It is the minimum intensity for reliable detection, the intensity that saves power in the marker's phosphorescent material without reducing the navigation reliability below the blackout protocol's design requirement. The markers glow. The darkness shows them. The passenger sees the green line below the pod's position and to the direction of travel. The navigation reference is established. The flywheel engagement. The flywheel was spinning before the power failure. The electromagnetic propulsion's smooth pod transit maintains the flywheel's coupling to the drive gear through the magnetic coupler's field, with the flywheel absorbing the speed variations from the maglev propulsion's cadence regulation. At the power failure's onset, the flywheel's rotational inertia maintains its spin briefly. The flywheel does not instantaneously stop when the electromagnetic propulsion ceases. The rotational inertia is the flywheel's kinetic energy, the energy the flywheel was storing from the electromagnetic propulsion's maintenance of the pod's transit speed before the power failure. The flywheel's kinetic energy is available to the mechanical drive's engagement immediately. The mechanical clutch's engagement converts the flywheel's stored kinetic energy to the drive gear's engagement with the guide rail's physical teeth, moving the pod forward at the velocity the flywheel's current rotational speed produces through the transmission's gear ratio. The initial mechanical drive engagement uses the stored kinetic energy rather than requiring the passenger to immediately begin pedaling. The pod moves from the flywheel's stored energy while the passenger assesses the blackout protocol's condition and initiates the pedaling sequence. The flywheel's stored energy is not unlimited. The stored kinetic energy at the power failure's onset depends on the pod's transit speed before the failure, which the electromagnetic propulsion was maintaining at the boulevard's operating speed. The kinetic energy produces forward motion at the mechanical drive's output speed for the duration the stored energy sustains against the guide rail's rolling resistance and the passage's hydraulic drag on the settled pod. The duration is brief, seconds rather than minutes, before the flywheel's rotational speed declines to below the minimum for effective drive gear engagement. The passenger's pedaling input supplements and then replaces the flywheel's stored energy. The pedaling begins before the stored energy is exhausted, adding rotational input to the flywheel at the cadence the passenger's aerobic capacity sustains, maintaining the flywheel's rotational speed above the minimum for drive gear engagement, and advancing the pod along the guide rail's physical teeth toward the nearest wetlock docking port. The pedaling's mechanical effort in the blackout protocol's conditions is higher than in the normal pedaling mode's recreational transit. The pod has settled from the maglev's zero-contact levitation onto the guide rail's physical surface, adding the rolling resistance of the pod's contact with the guide rail to the mechanical drive's propulsion requirement. The increased resistance is manageable for the blackout protocol's rated duration, the aerobic effort required to advance the pod at the blackout protocol's target speed against the rolling resistance, for the duration the soda-lime canister's remaining CO2 management capacity allows, is within the aerobic capacity that the Adventure program's scavenger fitness requirement establishes as the minimum for full blackout protocol self-evacuation. The fitness requirement is the blackout protocol's most explicit human physical specification. The passenger must be able to pedal the mechanical drive against the rolling resistance for the maximum estimated time to the nearest wetlock at the blackout protocol's target speed. The target speed is the minimum that maintains the pod's advance against the passage current's potential opposing force, the underground river's flow that the power failure has not stopped and that the pod is now advancing against or with depending on the passage section's flow direction. The passage section's flow direction relative to the pod's direction of travel is the blackout protocol's most consequential geometric uncertainty. The passenger does not know, in the absolute darkness, whether they are traveling with or against the underground river's current. The strontium illuminate markers show the guide rail's direction, but the guide rail runs in both directions from the passenger's position, and the markers glow in both directions. The nearest wetlock may be in the direction of the current or against it. The training protocol's preparation for this uncertainty is direct. In the event of direction ambiguity, the passenger travels in the direction the strontium illuminate marker's gradient indicates, the direction where the marker's density is higher, indicating proximity to a hub node's more frequently maintained section where the marker replenishment is more recent and the emission intensity is therefore higher. Hub nodes are where wetlocks are. Higher marker intensity indicates closer proximity to a wetlock. Higher marker intensity is the direction of travel. The marker intensity gradient is a simple navigation heuristic, not precise navigation to the nearest wetlock, but a reasonable directional indicator that the blackout protocol's passenger can apply in absolute darkness using only the rod photoreceptor's relative intensity assessment. The simple heuristic is more robust in the absolute darkness than a precise navigation system would be, because the simple heuristic requires only the comparison of two directions' perceived marker intensity, a task the dark adapted visual system can perform without the precision that more sophisticated navigation requires. The soda-lime budget. The soda-lime scrubbing canister is the blackout protocol's most critical consumable. The canister's CO2 absorption chemistry is passive, no power required, no activation mechanism, but finite. The canister's rated capacity is the total CO2 mass the canister absorbs before the soda-lime's reactive surface area is fully consumed, before the lithium hydroxide and calcium hydroxide in the soda-lime mixture has reacted with enough CO2 to reduce the available reactive surface to below the threshold that prevents atmospheric CO2 from rising above the immediately dangerous concentration. The canister's capacity in the standard blackout protocol configuration is sized for the single passenger's CO2 production rate at the elevated metabolic rate the blackout protocol's aerobic effort produces, not the resting metabolic rate, which the longevity program's sleep accommodations atmospheric management uses as the baseline, and not the moderate activity metabolic rate the recreational pedaling mode produces, but the elevated metabolic rate of sustained aerobic effort against the guide rail's rolling resistance for the duration of the maximum estimated time to the nearest wetlock. The maximum estimated time to the nearest wetlock is the blackout protocol's most important spatial parameter. It determines the canister capacity required, which determines the canister size, which determines the storage space the pod's standard configuration must allocate to the blackout protocol's consumable inventory. The maximum estimated time is derived from the crystal tube network spacing between wetlock docking ports, the maximum distance between adjacent wetlock positions in the freshwater zone's crystal tube network, divided by the blackout protocol's target speed, with the safety factor that the founding charter's life safety specification requires for the consumable's remaining capacity at arrival at the wetlock. The maximum wetlock spacing in the freshwater zone's crystal tube network is specified in the crystal tube standard as a safety requirement rather than as an operational preference. The maximum distance between wetlocks is not the distance that operational efficiency maximizes, which would be as few wetlocks as possible, each serving the longest crystal tube section, but the distance that the blackout protocol's canister capacity can sustain at the elevated metabolic rate. Every crystal tube section in the freshwater zone has a wetlock within the soda-lime canister's capacity at elevated metabolic rate, with the required safety factor, from every position in the section. The spatial constraint that the blackout protocol's soda-lime budget imposes on the crystal tube network's wetlock spacing is the network's most directly life safety-derived design parameter. Every other aspect of the network's spatial organization reflects the operational efficiency, the biological management protocol, the acoustic management, the visitor experience design, and the transit management optimization, all of which have been documented across the preceding parts. The wetlock spacing is determined by the soda-lime canister's capacity in the blackout protocol's elevated metabolic rate condition. The life safety requirement determines the spatial parameter. The spatial parameter determines the network's wetlock distribution. This is the blackout protocol's architectural contribution to the crystal tube standard, the requirement that imposes the wetlock distribution whose spacing the soda-lime budget determines. The wetlock is the crystal tube standard's most frequently encountered safety element from the visitor experience perspective, the docking port that the scavenger participant uses to enter and exit the crystal tube network, The destination the cycle sub standard transit uses for arrival at each hub, the access point the maintenance sub uses for cargo transfer. The visitor sees the wetlock as the transit system's interface. The blackout protocol sees the wetlock as the survival system's terminus. The same object. Two functions. The wetlock spacing serves the transit system's operational convenience and the blackout protocol's life safety simultaneously. The transit system's preference for wetlock positions at hub nodes, at junction nodes, and at waypoint accommodation sections coincides with the blackout protocol's requirement for wetlock positions within the soda-lime canister's capacity from every section. The coincidence is not accidental. It reflects the fact that the operational desirability of wetlock positions at network nodes and the safety requirement for wetlock positions within the soda-lime range from all sections both push toward the same distribution. The wetlock distribution is overdetermined by operational utility and life safety simultaneously. Overdetermination is the safety architecture's most comfortable condition. The provision that two independent requirements converge on is the provision that is most robustly specified, because removing either requirement still leaves the other specification intact. The CO2 indicator. The soda-lime canister's remaining capacity is not directly visible to the passenger in the absolute darkness of the blackout protocol's operating condition. The canister's chemical reaction does not produce a visible output. The soda-lime absorbs CO2 in a chemical reaction that produces calcium carbonate and water as products, both of which remain in the canister without any visible emission. The passenger cannot observe the canister's consumption state directly. The passenger can observe the atmospheric CO2 concentration through the pod's interior CO2 indicator, a colorimetric sensor that changes color in proportion to the atmospheric CO2 concentration, without requiring any electrical power because the colorimetric reaction is passive chemistry rather than an electronic measurement. The colorimetric sensor's color is readable in the blackout protocol's absolute darkness through the photoluminescent coating on the sensor's display surface, the same strontium illuminate chemistry that the guide rail's markers use, applied to the sensor's color change indicator face so that the indicator is readable by the dark-adapted visual system's rod photoreceptors in the absolute darkness. The indicator's color range spans from green at CO2 concentrations well below the physiological impact threshold, through yellow at the elevated concentration that the established safe working limit specifies, to orange at the concentration that the immediately dangerous short-term exposure limit specifies. The blackout protocol's operating guidance for the CO2 indicator is binary in its life safety application. If the indicator is green or yellow, continue pedaling at the current cadence. If the indicator transitions to orange, increase the cadence to reach the nearest wetlock before the CO2 concentration rises further. The orange indicator is the blackout protocol's most urgent behavioral signal, more urgent than the strontium illuminate marker's intensity gradient, more urgent than the pod's advance rate against the guide rail's rolling resistance, more urgent than the passage current's opposing force. The orange indicator communicates that the soda-lime canister's remaining capacity is approaching exhaustion at the current metabolic rate CO2 production rate, that the time to canister exhaustion is less than the time to nearest wetlock at the current advance speed. The passenger's response to the orange indicator is to increase the pedaling cadence above the sustainable aerobic rate, to the sprint cadence that the blackout protocol's training protocol identifies as the maximum sustainable for the estimated remaining time to the nearest wetlock at the current position. The sprint cadence increases the CO2 production rate. Sprint metabolic effort produces more CO2 per minute than the sustained aerobic effort, which further reduces the time to canister exhaustion. The increased advance speed partially offsets the increased CO2 production rate through the faster approach to the nearest wetlock. The net outcome of the sprint cadence is a race between the approach speed's reduction of time to wetlock and the increased metabolic rate's reduction of time to canister exhaustion. The race is won by the passenger who is closest to the nearest wetlock when the indicator transitions to orange. The blackout protocol's wetlock spacing specification ensures that this race is winnable, that the sprint cadence's increased advance speed produces a time to wetlock that is shorter than the sprint cadence's increased metabolic rate's time to canister exhaustion, with the safety factor the specification requires. The specification ensures that the race is winnable. The passenger must run it. The training protocol's preparation for the CO2 indicator's orange state is the most physiologically demanding component of the blackout protocol's training. The sprint cadence in the training simulation's elevated resistance condition, for the estimated sprint duration to the nearest simulated wetlock, at the elevated CO2 environment that the training protocol simulates to verify the participant's physical tolerance for the race's conditions. The training simulation sprint is the blackout protocol's most demanding human physical requirement. It is the requirement whose satisfaction confirms the passenger's fitness for unsupervised deep-zone crystal tube transit. Communication in the blackout protocol. The coordinating system's data network is offline in the blackout protocol's full power failure condition. The passenger cannot communicate with the coordinating system. The coordinating system cannot communicate with the passenger. The maintenance crew that the blackout protocol's onset should trigger cannot communicate with the coordinating system to receive dispatch instructions because the coordinating system's communication infrastructure is offline. The blackout protocol's communication is acoustic, the low-frequency acoustic signals that propagate through the cenote's water column and the crystal tube's structural material regardless of the electrical infrastructure status. The passenger in the pod in the blackout protocol's condition can communicate with any other person in the passage network through the crystal tube's structural vibration, physically tapping on the pod's hull with the specific coded pattern that the blackout protocol's training protocol teaches. The SOS pattern in the Cenote Communication Standards coding scheme produces acoustic signals that propagate through the water column and the crystal tube's structural material to anyone in the passage network with an acoustic propagation range. The acoustic signal's propagation range in the freshwater zone's crystal tube network is the passage geometry's acoustic waveguide effect. The crystal tube's circular cross-section and the passage's limestone walls together create an acoustic waveguide that propagates the tap signal's low-frequency content with lower attenuation than free field propagation in open water would produce. The SOS signal's first arrival at the nearest maintenance crew's position is their blackout protocol response trigger, the signal that initiates the maintenance crew's emergency response protocol, which includes the navigation to the signal's origin through the acoustic propagation's direction and the physical connection through the guide rail's physical teeth to reach the distressed pod's position. The maintenance crew's emergency response in the blackout protocol's full power failure condition is itself a blackout protocol operation. The maintenance sub's electromagnetic propulsion is offline, requiring the mechanical drive's engagement with the guide rail's physical teeth, and the coordinating system's navigation data is offline, requiring the strontium illuminate marker's navigation reference. The maintenance crew arrives at the distressed pod's position by the same navigation and propulsion systems the passenger is using: passive, power-independent, physics-based. The connection between the maintenance crew sub and the distressed pod is the mechanical tether, a physical connection that the maintenance sub carries as a standard blackout protocol equipment item, deployed from the maintenance sub to the distressed pod's tether connection point and used to transfer the distressed pod from its current position to the nearest wetlock by the maintenance sub's mechanical drive's propulsion against both pods' combined rolling resistance and the passage's hydraulic drag. The combined rolling resistance of two pods against the guide rail's physical surface, propelled by the maintenance crew's pedaling supplemented by the distressed pod's passengers pedaling if the passenger's physical condition allows, advances the coupled pods toward the wetlock at a reduced speed relative to the single pod's blackout protocol advance speed. The reduced speed increases the time to the nearest wetlock, but the mechanical tether connection also allows the maintenance crew's soda lime canister's remaining capacity to supplement the distressed pod's canister, extending the combined CO2 management capacity proportionally to the remaining capacity in both canisters. The combined resource pool is the mechanical tether's most critical benefit. The distressed pod whose canister is approaching orange indicator status is now connected to the maintenance sub's canister, whose capacity may be substantially higher than the distressed pod's if the maintenance crew's blackout protocol response was rapid. The combined capacity's time to exhaustion at the combined two-person elevated metabolic rate is the relevant constraint. The combined time to exhaustion is the blackout protocol's survival horizon. The combined advance speed is the wetlock approach rate. The race's outcome is determined by which is shorter, the combined time to exhaustion or the combined advance time. The mechanical tether and the combined resource pool are the blackout protocol's most explicitly social provisions. The survival outcome in the blackout protocol's most resource-stressed scenarios depends on the maintenance crew's rapid response and the physical connection that combines the distressed and rescue pod's resources. The individual blackout protocol's passive systems, the strontium illuminate markers, the soda lime canister, the Avalo system, the flywheel mechanical drive, sustain the individual passenger through the standard blackout protocol's duration. The social blackout protocol's mechanical tether and resource sharing sustain the individual passenger through the extended duration that the maintenance crew's assistance provides. The scaphander in the blackout protocol. The scaphander participant in the open freshwater zone during a full power failure is in a different blackout protocol condition than the pod's passenger, outside the crystal tube network's atmospheric enclosure, inside the Cenote's water column, with the alone visor's emergency AR overlay providing the strontium illuminate marker's position reference and the rebreather's remaining capacity as the survival horizon. The scaphander's blackout protocol is simpler in one respect and more complex in another. Simpler because the scaphander participant is already in a self-contained atmospheric system, the closed-circuit rebreather, that is not dependent on the crystal tube network's atmospheric management infrastructure. The rebreather's power failure effect is the loss of the display monitoring's electronic functions, the remaining canister capacity indicator, the oxygen partial pressure display, the dive depth display. The mechanical functions, the breathing gas flow, the CO2 scrubbing chemistry, the pressure regulation, are passive and continue without electrical power. More complex because the scaphander participant in the open water column has three-dimensional freedom of movement that the pod's guide rail constrains. The participant can move in any direction, which means the navigation requirement is more demanding than the guide rail's two-direction constraint. The strontium illuminate markers that the alone visor's passive optical sensor detects are the guide rail's markers, at the crystal tube network's guide rail position in the passage below the participant's current depth. The participant must descend to the guide rail's depth to use the markers as a navigation reference, then navigate along the guide rail's marker sequence toward the nearest crystal tube section with a wetlock. The descent to the guide rail's depth in the blackout protocol's absolute darkness requires the Avalo system's manual buoyancy trim. The participant reduces the bladder's compressed gas volume, reducing buoyancy below the participant's current positive buoyancy state, and descends through the dark water column toward the guide rail. The descent is not directed. The participant descends vertically until the passive optical sensor detects the strontium illuminate markers below. The descent in absolute darkness with no visible reference other than the marker's eventual detection requires the trained participant's behavioral composure. The darkness is not evidence that the descent is proceeding incorrectly. The marker's detection is the evidence that the descent has reached the guide rail's depth. The participants who have completed the blackout protocol scaphandre training are the participants who have descended to the guide rail's depth in a simulated blackout protocol condition and detected the marker's passive optical sensor reading in the training environment's controlled absolute darkness. The trained response is established before the actual blackout protocol's occurrence. Descend to guide rail depth, detect the markers, navigate along the markers toward the nearest wetlock, dock through the wetlock standard procedure at the external hatch, complete the pressure equalization, and enter the crystal tube's atmospheric interior. The docking procedure at the wetlock in the blackout protocol's condition is the scaphandre participant's most demanding operation. The wetlock's docking port's lone conical reception disk is a specific geometric target in the absolute darkness, detectable by the scaphandre's passive optical sensor through the strontium illuminate marker's identification of the wetlock's position in the guide rail's marker sequence. The wetlock position's marker pattern is differentiated from the standard 100-meter marker pattern by a specific spacing deviation that the training protocol teaches participants to recognize. The wetlock's docking port is also the emergency optical identification feature. The wetlock's external conical surface carries a higher density of strontium illuminate coating than the guide rail markers provide, producing a localized higher intensity phosphorescent glow that the dark adapted visual system can resolve at the approach distance the docking protocol requires. The glow is the wetlock's blackout protocol beacon, the passive, power-independent position indicator that the approaching scaphandre participant can use to identify the wetlock's exact geometric position for the nose cone alignment sequence. The nose cone alignment sequence, the seal inflation, the water evacuation, and the pressure equalization are all mechanical procedures that the blackout protocol's power failure does not disable. The wetlock's docking sequence is designed to complete through passive mechanical and chemical systems that do not require electrical power. The seal inflation uses the dock's atmospheric pressure, which the isolated compartment maintains through its own resource inventory. The water evacuation uses the vacuum pump's stored vacuum reservoir, not the electrical pump's active generation. The pressure equalization is passive diffusion through the equalization valve's mechanical opening. The scaphandre participant who has navigated from the open water column to the wetlock in absolute darkness has completed the blackout protocol's most demanding individual survival sequence. The sequence's completion delivers the participant to the crystal tube network's atmospheric interior, the compartment whose resource inventory provides the self-sufficiency period that the Terraform operator's breach event assessment and repair protocol is designed to complete within. What the blackout protocol produces. The blackout protocol's 5 passive systems, the strontium illuminate navigation markers, the soda-lime CO2 scrubbing canisters, the Avalo system's manual buoyancy trim, the flywheel's mechanical drive coupling, and the supercapacitor magnetic braking's independent power supply, are the blackout protocol's specific design provisions. But the blackout protocol produces something beyond the physical survival capacity these provisions enable. It produces the specific knowledge of what the formation is like without the civilization's technology. The passenger who has navigated the blackout protocol's conditions, who has pedaled through absolute darkness by the green marker's guidance, who has managed the CO2 indicator's color through the sprint cadence's physiological demand, who has arrived at the wetlock's phosphorescent beacon and completed the docking sequence through passive mechanical procedures, has experienced the cenote as it was before the light relay's illumination and the electromagnetic propulsion and the coordinating systems navigation. Not as an accident to be recovered from. As a reality to be navigated. The formation is what the blackout protocol reveals, the geological structure that the guide rail traverses, expressed in the strontium illuminate marker spacing, the absolute darkness that 66 million years of geological isolation produced, the water column's hydraulic resistance that the flywheel's mechanical drive pushes against, the CO2 chemistry that the passenger's metabolism is doing and that the soda lime is absorbing. All of this is the formation, present in the blackout protocol's operating conditions without the technology that normally mediates the passenger's experience of it. The blackout protocol is the formation without the mediation. The safe navigation through the blackout protocol is the proof that the civilization has built its survival capacity into the formation's conditions rather than into the technology that the formation could eliminate. A civilization whose survival depends on its technology is a civilization that the formation can eliminate. A civilization whose survival provisions are the formation's own physics. The strontium illuminates phosphorescence from the guide rail that the formation's geology required, the soda lime's chemistry that the passenger's metabolism drives, the Avalo system's compressed gas that the formation's hydrostatic pressure makes effective, the flywheel's kinetic energy that the formation's guide rail is the medium for, is a civilization that the formation cannot eliminate, because the survival Provisions are the formation's own physical reality organized by the civilization's design. The blackout protocol is the test of whether the civilization has built its safety provisions from the formation's physics or from the technology the formation could remove. Pipe dream passes the test. The markers glow. The canister absorbs. The flywheel drives. The scaphander descends to the guide rail. The wetlock's beacon identifies. The passenger arrives. The formation is still there. The civilization is still inside it. The restoration protocol. The blackout protocol's operating phase ends when the power supply is restored, when the streaming potential harvests direct generation, supplemented by the backup power systems that the formation events cause analysis determines can be safely restored, returns electrical power to the crystal tube network's infrastructure. The restoration is not automatic. The full power failures cause must be assessed before the electrical systems are restored, because the cause may be the formation event that the safety architecture's failure response has managed and whose resolution the terraform operator's post-event assessment authorizes, or it may be the ongoing geological condition that the electrical system's restoration would expose to the formation event's active hazard. The restoration sequence is initiated by the terraform operator's concurrent authorization. The assessment confirms that the formation event's primary hazard has been managed, that the collar failure's affected section is isolated, that the gate seal is maintaining the atmospheric isolation, and that the electrical system's restoration will not expose any uninvolved section to the hazard that the isolation is managing. The restoration authorization releases the coordinating system's emergency management layer to restore power to the unaffected sections of the crystal tube network, beginning with the section that contains the maintenance sub and the distressed pods in blackout protocol condition, and to restore the atmospheric management systems, the light relay, and the transit management system in the sequence the restoration protocol specifies. The restoration is not a single event restoration of the full network simultaneously. The sequence restores power section by section, confirming the safety status at each restored section before proceeding to the next, rather than restoring the full network simultaneously and discovering that a restored section's safety status is compromised after the restoration. The sequence's conservatism is the restoration protocol's most important property. The restoration that discovers a compromised section's safety status after restoration is the restoration that has introduced the additional risk of operating equipment in the compromised section's proximity. The restoration confirmation at each section before proceeding is the REDIWA framework safety governance requirement for power restoration. The terraform operator's concurrent authorization at each section's restoration confirms the section's safety status from the post-event biological and structural assessment before the electrical systems that could interact with the section's hazard are restored. The confirmation gates the restoration. The restoration gates the return to normal operation. The normal operation's return is the blackout protocol's resolution. The passengers who navigated the blackout protocol emerge from the wetlock's atmospheric interior into the restored crystal tube network's illuminated passages. The light relay's photosynthetically active output has returned. The coordinating system's navigation display shows the network's current configuration. The atmospheric management system's fans have restored circulation. The passage outside the hull is lit. The absolute darkness is the cenote's geological memory. The restored illumination is the civilization's presence in it. The passage between the two is the blackout protocol. The civilization navigated it. Part 7 Synthesis. The 5 chapters of Part VII's safety architecture are the civilization's honest accounting of what it has acknowledged about the formation it inhabits and what it has built in response to that acknowledgement. Chapter 1 acknowledged that the formation produces geological events. It built the breakaway architecture that manages the kinetic energy those events produce. Chapter 2 acknowledged that geological events produce breaches. It built the automatic bulkheads that seal those breaches without the sensor latency that the breach's development timeline precludes. Chapter 3 acknowledged that breaches can cascade. It built the compartmentalized city whose spatial organization contains the cascade within zones whose self-sufficiency periods the population management can sustain. Chapter 4 acknowledged that managed failures are the safety system's success. It built the living through failure culture that learns from managed failures and improves the management quality across the design life. Chapter 5 acknowledged that the power that manages the formation could be eliminated by the formation. It built the blackout protocol from the formation's own physics, passive provisions that the formation cannot eliminate because they are not the civilization's technology but the formation's physical reality organized for survival. 5 acknowledgements. 5 responses. 1 integrated safety architecture built on the premise that the formation is right, the formation will produce what it produces, and the civilization's safety depends on being correctly built for the formation rather than correctly positioned to prevent what the formation does. The formation is the cenote. The cenote is 66 million years old. The safety architecture is the civilization's response to 66 million years of geological production. The civilization is inside it. The safety architecture makes the inside safe. That is the safety architecture's entire purpose and its complete achievement. Cross-references, Part 2, CH4, The Crystal Tube Standard, Part 3, CH1, Rivers Beneath the Jungle, Part 6, CH1, Pedal Submarines, Part 6, CH2, Scaphanders for Everyone, Part 7, CH1, Breakaway Architecture, Part 7, CH2, Automatic Bulkheads, Part 7, CH3, Compartmentalized Cities, Part 7, CH4, Living Through Failure. For Blackout Protocol Passenger Training Simulation Protocol and Physical Fitness Confirmation Requirements, see Appendix H, Governance Operations Manual. For Strontium Illuminate Marker Emission Calibration and Wetlock Beacon Differentiation Pattern Specification, see Appendix D, Construction Operations Manual. For Soda-Lime Canister Capacity Specification and CO2 Indicator Colorimetric Sensor Calibration, see Appendix D, Construction Operations Manual. For Mechanical Tether Deployment Protocol and Combined Resource Pool Management Guidance, see Appendix D, Construction Operations Manual. For Power Restoration Sequence and Terraform Operator Concurrent Authorization Protocol, see Appendix H, Governance Operations Manual. End of Part 7, Safety First. Discussion about this episode. Comments. Res Tax. Recent episodes. Sueño de Tuberia Part 3. 15 hours ago MXTM aka Pirate 1 or VJ'd Cinema X. Pipe Dream Part 6. July 12 MXTM aka Pirate 1 or VJ'd Cinema X. Pipe Dream Part 5. July 12 MXTM aka Pirate 1 or VJ'd